Hello, sir. Good afternoon.
Yeah, good afternoon, madam.
Good afternoon, sir. So we'll start with this session. So let me just take a moment to introduce you and welcome the participants here. So good afternoon, everyone. A very warm welcome to all our participants who has joined us on the sixth day of the Atal AICTE sponsored 6-day faculty development program on seismic vulnerability assessment organized by the Department of Civil Engineering, Royal School of Engineering and Technology, the Assam Royal Global University. We are delighted that today we arrive at the final day of this academic journey, and we have three highly accomplished speakers lined up for today who bring with them immense expertise and experience. Our first technical session of the day is to be delivered by Dr. Nirmalindu Devnath. Dr. Nirmalindu Devnath is presently working as an associate professor in the Department of Civil Engineering at NIT Silchar, additionally serving as associate dean, planning and development, and chairman of Tender Evaluation Committee for Institute Works. He is specialized in structural engineering, who earned his PhD degree from the Indian Institute of Technology, IIT Guwahati, following a master's degree MTech in structural engineering from IIT Guwahati and a bachelor's degree BTech in civil engineering from NIT Agartala. Besides working at NIT Silchar, his other primary experiences were working with Tejpur University as an assistant professor, software engineer in the structural engineering domain, in Bentley Systems, dealing with the STAD Pro software. He has completed one SCRBDST funded R&D project during 2016 to 2019 under the as Young Scientist Scheme as sole investigator, and one SCRBDST funded R&D project during 2021 to 2025 under the Core Research Scheme as principal investigator. During working with NIT Silchar, Dr. Devnath has completed guiding 5 PhD students. Besides, he has established a laboratory in NIT Silchar for modal testing facility. The areas of expertise and interest of Dr. Devnath are primarily structural vibration and control, modal testing, finite element model updating, structural health monitoring, and seismic performance and retrofit. We are delighted to welcome you, Dr. Nirmalindu Devnath, sir, to our FDP and look forward to your insights. I hand over the session to you.
Yeah, thank you very much, madam, for the invitation. And mm, also, I like to congratulate uh, Dr. Yeah, madam, uh, Dr. Shoteshwara Barma, mm, and Mr. Rishikesh Darwa. So, respectively, professor and assistant professor in the Department of Civil Engineering at Royal Global University, for this receiving the fund for this 6 days uh, workshop and faculty development program. Okay, and so now I like to uh, start my presentation. Okay, so I'm sharing the screen. Uh, I hope my slides are visible.
Yes, sir, it is visible.
Visible, huh?
Yes, sir.
Okay. Uh, so the topic so I'm discussing here today is the structural health monitoring. And so since it is a uh, primarily a faculty development program uh, dealing with that seismic vulnerability. So so many things are uh, become associated uh, apart from your assessment of vulnerability. So at the same time, we are also uh, become get concerned for the health monitoring, retrofitting. Uh, so many things are there. So one of these very important associated uh, mm, matter here is the structural health monitoring. Uh, so I'm uh, discussing uh, here today. Uh, so before beginning, I once again uh, congratulate and thank Dr. Sotembara Bharma, Madam, for inviting uh, and also doing this FDP, uh, which can motivate many to work in this domain, which is very important, uh, especially for the northeastern part of India. Uh, so the structural health monitoring, from the name itself, we have a very good sense of it. So we're basically monitoring the structural condition. Okay, so this
Mm.
thing, the structural health monitoring is not very new term. Okay, and
Hmm.
mm, uh, but the motivation is not quite old. Uh, so this is a very uh, usual motivation. We understand. Uh, Traditionally, we do a study in civil and any other engineering, relevant engineering, uh, about this non-destructive testing. Okay, so
Uh,
I hope.
very sorry to interrupt you, sir.
Yes,
Uh, Sir, your slides are not coming in full screen mode, sir.
is it? But here it is in my full screen mode. Is it now okay?
Uh,
No.
Again, it is coming in some kind of thumbnail mode, sir. Is there any option for full screen, sir, there itself?
Sir,
During
let
during
me
share.
help you with this. Please turn on the slide sharing option. I mean, go to the presentation mode so that I can guide you further. Like, go
I'm
to your
actually,
presentation first.
yeah, in this page only.
No, no, sir, your PPT presentation. Please turn on.
Okay, okay. Yes, 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 yes.
Then go to PPT mode, like
PP,
the way you did last time.
PPT mode.
Yes, the icon
Third
there.
option, sir. Third option, sir.
No, no,
Acha.
the next option. I mean,
Yeah, yeah. This one, na?
yes, sir.
Yeah. Slide view.
Click.
Yeah.
Okay. Okay. Now, please select the display setting in the top second option.
Okay.
Now, just duplicate the slideshow. Then you'll get into the
I
full
have to
screen.
click it.
Yes, sir. Please click. Yes, sir.
Yes,
Now
sir.
you can move further.
Okay. 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 Thank you.
Yes, sir. Now it is in full screen mode, sir. We can
Okay.
proceed, sir.
Yeah, yeah. So it is all right. Thank you.
Thank you, sir.
Okay. uh, so as a discussing that the motivation is very old. Uh, all the civil engineers, even in undergraduation, mm, are aware of this NDT, non-destructive evaluation. Uh, so motivation is to some extent the same, but uh, structural health monitoring has become much more uh, mm, sophisticated technically. Okay, so most of the case, the formally we say that uh, so any your assessment or evaluation of health of structure, if you do on the continuous basis, so that is a very important thing, continuous basis, continuously, then we uh, typically we consider it under the structural health monitoring. Okay, so say many techniques we use, so like ultrasonic pulse velocity, rebound hammer, so these are quite usual in the structural practice and civil engineering studies. But those are not a continuous event, means we do it when we like to do. So typically these are not considered, although having the similar motivation for that. So here are the some of the basic highlights I'm going to cover here. So this health monitoring is, as I said, we understand. Um, okay, we have very good sense even from the topic itself. Uh, so this is nothing but your uh, in service, when the structure is in service. So we're continuous basis, continuum, sorry, continuous time basis. We are assessing the structure which is in service. So this is basically structural health monitoring. Okay, so continuous time basis is the important thing, which makes it different from NDT. Now, uh, so what is the purpose? So purpose is well understood, the safety basically. Okay, to detect the damage. Then if we find the damage, then we can find uh, yeah, so damage in various strategy, we'll look into it. And if we find the damage, then we can do repair, we can do rehabilitation. Okay, there is scopes are there in case we can find some sort of damages. So basically this is nothing but our safety. So safety is the fundamental thing. So here we understand. uh, Now here are the few of the questions. mm, why indeed the disaster happen. So even if we do design, we have studied so many courses for structural analysis uh, designs. Okay, so uh, so what so many of us are doing or have developed specialized or have been specialized on design. Okay, so that so at this stage we understand that in this process there is various uncertainties, assumptions, many things are there. So so we can't ensure that mm, uh, in a design that it is completely safe. Okay, so design uncertainties is there. Then loading uncertainty. So we find a load up to certain we estimate in this in many cases in probabilistic way that with the confidence level we're considering the load. Okay, uh, our target load. So obviously there are uncertainties, we can't mm, ensure the intensity of the future any loading event. Okay, including earthquake. So earthquake is the major thing of our concern basically, at least in northeastern region. Wind is concerned, but probably not earthquake is a matter of um, our concern is more with earthquake instead of wind in northeast. Um, um, and then manufacturing uncertainties, and which we mostly uh, we consider as a workmanship in civil engineering. And then material variations is there. We know that suppose sometime uh, mm, especially in civil engineering, when we're working with the concrete, so we also know that the partial safety factor of the concrete is quite higher, because there is lots of scope of or possibility of material variations. But when you work with steel, then our factor of safety is quite less, because we're much confident about this. All right. So there is so many uncertainties. Then environmental variations is also a factor. Okay. And then apart from that, aging effect. So with aging, uh, mm, some materials are less, some more susceptible for your damages. Okay, so there's the primary factors, so why damages happens. Okay, so there are many examples of damages, but here are a few examples I'm showing here, which were designed properly. Okay, so if some thing is not uh, well designed, and so mm, so that damages happen, so that is not a concern. But when some structures are designed well, um, then is a concern for us, obviously. um, Here we can see some example here. Here it is your one bridge. So this one example that many reported uh, the shock of damage. And okay, so the next example is one aeroplane accident. So aeroplanes are uh, designed, are constructed with utmost safety measures. So um, so safety is a dominant uh, factor in the design of aerospace structures. But still, there is one event happened in 1998, when a flight, actually it is, there is a structural failure. Fortunately it landed fine. So however, so here is our concern is that even you're doing so good design, but the thing uh, shouldn't end only after the construction. Okay, so we need the uh, monitoring or assessment of the structural condition. We typically say also structural health. Okay, and there is a third example. So might be if some one already have seen it, but but who have not seen it, you may find very astonishing. So it's just small a video, you may look into it. I'm just playing it.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
All right, so it is a very astonishing and event. So obviously these sort of bridges are designed very well, and so this bridge actually collapsed due to wind load. And so you have noticed in the video that there is not any storm was there at the time. And so this bridge has collapsed with a very moderate under wind condition, but the intensity of the wind was moderate, but the 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 pattern of the wind was something different. The pattern of the wind is something like this, which uh, was responsible to excite the structure uh, around its fundamental frequency, so which caused resonance. Okay, so there is some sort of discussion we'll make it here today. So resonance, probably many of are aware of about it. So resonance is when you excite a structure around its with some frequency content around its natural frequency, then it is intensity of vibration become uh, significantly, sometimes you can say abnormally higher than the usual. So this is the, in a generic way, if I represent, or very easy way, so this is the resonance. So that resonance happened for this structure. Okay, and so so we've understood that our engineering is not limited with the design and analysis. Okay, and so again we are, as I discussed, that it is our target on a continuous basis. Okay, and so with the development of the computation power, development of the uh, so many development have happened today till date on computation, then electronics, sensing technologies, communication, information technologies. So things have very now accessible to us, and so we have a continuous level monitoring is basically is not a big mm, anymore. Okay, it's not a very big thing anymore. So in this continuous measurements, so when you're doing this assessment, so basically we need to measure something. So for that we need sensor. So sensor, usually sensor, or we call it transducer also. So it uh, it will give you the information about the any quantity would like to understand. Then so that sensor information we have to record it. Okay, then we have to, so this is our basically the data, and then we have to interpret, process, analyze the data, to understand that uh, what is the assessment, what is the condition, or what is the health of the structure. Okay, and even there is a scope for real time mm, take we can take action in real time. For that we have actuators, controllers. Okay, uh, so structural health monitoring is a nowadays a very interdisciplinary and a very promising domain. Um, and and many nowadays many working with doing research in this domain along with myself. So this the health monitoring, basically the we're assessing the condition of the structure. So here there is a analogy with human being. So this is well understood. Um, and so today today in India we are doing the practice. Uh, in there is multiple examples, major examples where health monitoring exercise practice is do exist today in India. Uh, mm, However, some countries like Japan already they're doing it for a longer time. We know that Japan is so much vulnerable to major earthquakes. So in Japan, there is this sort of monitoring, health monitoring, then even real time uh, uh, actions, okay, like uh, active, semi-active controls. There is many uh, many occasions of practices in Japan we do see. So this is one example. Okay, uh, so when you do that census continuously monitoring, then you are also additionally we're also ready with your actuators mm, to rectify, okay, as much as possible, take action on real time as much as possible. So these are basically one sort of uh, uh, we call it the smart structure. Okay, it sounds also very good, and they're really smart because uh, they measure the process and they take action. Okay, uh, so there are many examples. Even we can see in the literature. Meaning the literature means there is the scientific publications. Okay, we can see all this information we take basically from these scientific publications. Uh, mm, so here there is. We can see an example of a Guangzhou. There is an Canton Tower. It is one of the popular structure. So they're also practicing for assessing the structural health on continuous basis. Okay. Mm, so Eh, so as you said that uh, not only assessing, we not also to keep ourselves restricted up to assessing the structural health, we also along with like to additionally uh, take action in the real time. So here it is some passive and active SHM, uh, some author categorized like this, and we this so we need actuator for active SHM. So now let us have more discussions on directly on this the structural health monitoring practice. Okay, uh, so there is a very fundamental classification in structural health monitoring. Mm, so one is the global, another is the local. Okay, um, and so local is something we also call direct, um, uh, where we uh, mm, uh, assess the structure, okay, in the very vicinity of your measurement location. Okay, means suppose uh, I'm saying in this way, say you are using the suppose ultrasonic pulse velocity. Okay, so we are using it is a common NDT device, So NDT, as I said, NDT health and structure health monitoring, the motivation is not indifferent. They're quite similar, although the approach is different. Okay, now you're assessing uh, the uh, the condition using ultrasonic uh, pulse velocity meter. Then, uh, so while the part of the concrete you're using for passing your pulse, okay, so you can only assess the condition of that part of concrete only, isn't it? Now, so these are actually type of local level structural health monitoring. Now, the global level health monitoring is actually uh, mm, uh, something uh, different to it. So there, the the location of measurement uh, maybe maybe different means uh, means say I want to assess the structural the health. Suppose for any I'm targeting say particular say particular column. Uh, now my measurement, obviously I needed some measurement, you know that. So it's not necessary that I'm taking the measurement anywhere in the column. Okay, so maybe measurement is at different locations. Okay, so these are your global structural health monitoring. And so these are uh, uh, this strategy, this global level structural health monitoring, uh, it depend on the global signatures of the structure. Okay, and some other is the local. Okay, so local where your so have to assess say a beam column joint have to assess the condition of the concrete. So then you need to take your measurements. So for this region only. Okay, so so global is, so both are important to us. um, and um, if we can properly use the global health monitoring, global level which facilitate for the global level structural damage detection, then actually it gives a good help in assessing the possible locations of highly vulnerable locations. Okay, so there we can do in more further details, we can perform more local level structure health monitoring practices on the uh, vulnerable locations. So, and those vulnerable locations can be estimated well using the global level structural health monitoring. Um, so global level, when you say the global level structural health monitoring, so which depends on the global behavior. Okay, I'm giving a very small uh, discussions here additionally. See, um, say uh, the structural system uh, we describe uh, using the mass matrix, using the stiffness matrix. Okay, so that makes your system. Okay, and uh, and these are actually global. Okay, means uh, why it is global. Say uh, there is a, if I change the stiffness of a column of any part of a, say, a building, suppose, uh, or a member in a truss, say, I've changed the stiffness of a, say, bottom chord of a truss beam, sorry, a truss structure, sorry, a truss structure, then your stiffness matrix overall is going to be changed. Okay, and if that stiffness changes, then what will happen? Your natural frequency mode shapes are going to be changed, because the natural frequency and mode shapes depends on the mass and stiffness matrix. Okay, we don't know about it. uh, Now, also, also, if we look at the equation of a motion, uh, which also incorporate the mass matrix, stiffness matrix, in addition to that, one damping matrix. All right. So, uh, suppose in a building, suppose in a, say, a five-story building is there, and we have changed the say, the stiffness of a column in say, in the ground floor, then your mass and stiffness matrix is changed. Mass matrix is unchanged, but as a system it is changed, so stiffness matrix is changed. Now if you give some excitation, okay, so there will be change. Okay, uh, say you are exciting the undamaged case and damaged case, okay, of a structure under a same excitation, okay, under the same, maybe a same earthquake. So what is going to happen? uh, there will be change in the vibration. Okay, so that change in vibration is not limited to the location of the column. Okay, if you measure the vibration anywhere of the structure, okay, uh, although the damage only happened in this ground story, even you measure the vibration at the top, means at the roof, but still you'll see that there is a change in the vibration, okay, signature, comparing to the is undamaged, uh, while the undamaged and damaged both are excited under a same excitation. Okay, I hope it is understood. The So these are actually very interesting, a domain uh, where you can assess the location of the damage in a structure. So okay, so these SHM techniques, so there are various techniques for this SHM. Okay, so uh, not only your vibration, not only the eigen natural frequency mode shapes, even the strain. Okay, strain also is a the uh, your a global behavior. Okay, uh, so strain is also going to be changed. If there is, even there is only a particular member, it is stiffness degradation, but these that is actually influence the overall stiffness matrix and also
अपने
the
ब्रांड चेंज वाले हैं क्या बच्चे? चेंज आया था एक्चुअली, ये कल बीच में देखिए पूरा था कराना ये वाला नोटिस दिखा लूं कल.
okay, can you hear me?
Yes,
Yes,
sir.
right. Yes, sir.
Okay, okay. So I think it's all right. Um,
Sorry,
all right.
there some participants was
Acha,
unmuted.
yes,
Yeah,
yes, yes,
therefore.
yes,
So
yes, yes.
you may
Okay,
please continue, sir. Thank you.
yes, yes. So there is various techniques. So I think my slides. Okay. Um, yes. So there are many techniques. Okay, and many multiple local techniques, and there are multiple global techniques do exist today. Okay. Uh, So when you're looking at taking for this global, then natural frequency mode shapes, then this vibration signatures, then strain signatures. So these are mostly we consider. And for local level damage detections, there are many are there. Mm, there's many techniques, including ultrasonic, then acoustic emission, uh, mm, wave propagations, mm, mm, different type of wave propagations, etc. And so one thing we shouldn't disregard, or that is the visual observation. Okay. And so probably this is one of the very the oldest method, but still it is followed today. Okay. um, all right. So as I discussed that the non-destructive evaluation and the structure health monitoring is a quite a, under this similar motivation almost, although these typically different for this requirement of continuous basis measurement. Uh, so this is one mm, uh, uh, a discussion. So where a conventional ultrasonic uh, non-destructive evaluation, uh, we can also make it uh, continuous basis to incorporate as structural health monitoring uh, and practice. So, and this is ultrasonic pulse. Okay. So this thing also we can, so we did, we studied all this. Okay. Uh, and so this we know that it is not the continuous basis, isn't it? So we do when we need. So but that also we can do it continuous basis, isn't it? We need uh, so that also we can integrate to structural health monitoring practice. Okay. So here in this topic, I'm mostly discussing on this, the global level structural uh, damage indices. Okay. So in the global level damage detection, so as we discussed that we're not bound to, we don't need to uh, so first know the location of the damage, or guess possible damage location before doing the testing. Okay. So it is not exactly like this. So here we measure uh, uh, or do our measurements at various suitable locations. Okay. After all those measurements lead to you the possible location for the damages. Okay. So this is the global level damage detection. Mm, uh, so so when so nowadays there is a many requirements for practice of structural health monitoring. So mm, so so we so many of us actually need to um, try to develop uh, uh, expertise or area of interest in this domain. Uh, in this regard, uh, there are some few levels of damage detection, especially I'm saying the global level damage detection. So what we need to uh, take into account actually. So the first target is that uh, whether the structure has damage or not, to understand. Okay, so this is a the target is not uh, very hard. Okay, then second target is little high target, that the location of the damage. The third target is the quantification of the severity of the damage. Okay, and so this is very promising if we can do well. That if the This can be very much helpful in the structure. If there is a damage, we can find the location and the quantification of the damage, content or extent of damage. Uh, then finally, the evaluation of this your service life or remaining structural integrity risk assessment. So in this regard, a few things I'm quickly just uh, it is an interdisciplinary domain. So so many things uh, so one need to understand from out of typical civil engineering. Uh, so here this the first of thing is a sensor, then data acquisition. Okay, uh, so when you do the data acquisition, then we need to do follow some sort of uh, mm, considerations. I'm quickly mentioning all this. If you're doing already, then or you're thinking to do, then it may be helpful. Uh, so in this data acquisition, so this is a data acquisition system. So what it does actually, you might have heard of data acquisition system. Uh, so when you measure some quantity now, uh, say for this global level damage detection, the most uh, uh, popular choice is the measurement of acceleration. So that we need sensors in the form of accelerometer. So accelerometers are mm, uh, measurement is convenient, easy, okay, uh, mm, and we do have so many options in the market for accelerometers. Okay, even our smartphone is having also an accelerometer. So maybe those are not mm, uh, mm, the accuracy level is not that good. Okay, we need higher accuracy level. Okay, so this say quantity accelerometer, physical quantity, so these are continuous in nature. So obviously when something is continuous in term with respect to the time, so obviously it's not possible to take the data or to quantify it, isn't it? So theoretically do it, but when you have to measure it, so uh, we have to uh, uh, um, define or express the intensity of the signal, any signal, at a given point of time, every time points. Okay, so we are bound to mm, so take the data uh, at discrete time points. Okay, so say after some seconds. Okay, for example, many of us know about the El Centro earthquake, a very popular choice in this academics. Okay, so when it is recorded, okay, so typically these are recorded 100 points per second. Okay, now if we want uh, more accurate representation of the physical signal, then you can increase your number of data points per second. Okay, uh, all right, so we need the discrete representation. Okay, so and so that is the most important thing. So other part also, we need to take into account, say signal conditioning means uh, mm, so one thing as a health monitoring person, we should uh, take care about this so that your sensors get proper power supply, because sensor need power supply to operate. Okay, otherwise it's going to give wrong results. Okay, and then after that it is an analog to digital conversion. So this is analog signal, so as I said, discrete time, so you have to express in discrete form. Okay, so here mm, some thing we should note here, if somebody is starting think about experimentation, that the analog to digital conversion, so that there is a two thing here to note here. So one is bit depth, another is the your sampling rate. Okay, so sampling rate I just mentioned here, say 100 hertz typically we do in earthquakes most of the time. uh, and your mm, uh, bit depth, so bit depth is important, means uh, say some cases you can find 8 bit, so you, sometimes you feel that so it's very cheap data acquisition system. I mean, cheap means low cost. Okay, and sometimes it is looks very costly. So why it happens actually, so those things, the accuracy, so for accuracy, so your signal condition should be good, your analog to digital conversion bit depth should be higher. Okay, uh, so in this health monitoring practice, the 24 bit uh, is a we can say a benchmark for quality. Okay, if you go for more than 24 bit, then it will be obviously much more costlier. Probably is a trade-off, we can stop here 24 bit. Below 24 bit, say 16 bit, some cases we get some manufacturer 8 bit, so 8 bit you may not go to very good results if the structure is more complex. Okay, and regarding the sampling rate, um, so sampling rate, you have also you have to take care of it. Means one very very say your structural frequency content is say uh, suppose say 25 hertz. Okay, means all the modes and are within predominant modes are within 25 hertz, then there is a consideration of Nyquist frequency, then you have to, so this is a very typical term you will face if in this domain Nyquist frequency. So you have to take the data twice of this target frequency content, means at 50 hertz. Okay, so this thing, one should take care for data acquisition. and and also one thing to be taken care of, the data synchronization. Okay, because nowadays uh, we can see the IoT, uh, mm, so processing are not done, say, on this on site. So data communicated to the cloud, and from the cloud we uh, process the data to understand the or assess the health of the structure, or assess the condition. And this communication, there may be wired or wireless mode, whatever it is. So if you uh, the data synchronization is important, that uh, and so here we have uh, various types of sensors. Okay, sensing technologies. Okay, uh, mm, so there are many, obviously, so I'm not going through everything. So since predominantly people are using accelerometer, I'm just mentioning quickly here. So in this accelerometer, uh, two sensing technologies are quite prominent. One is MEMS. Okay, uh, so micro electromechanical sensing. Okay, MEMS. And another is piezoelectric sensor. So if you search, means you are interested, probably you are already doing it on it. um, so so MEMS, piezoelectric, so both are good, but MEMS is better uh, in some considerations. So mm, uh, you can do calibration is in very easily uh, using the MEMS sensor. So MEMS little bit costlier in general, however, mm, but in today there is many options are there. Okay, uh, so if you're working on it, so so the calibration aspect also to be taken care of, because these are the key to of your accurate data measurements. If data is not accurate, then your analysis obviously uh, mm, is not going to be uh, considerable. So this is a typical diagram, which is in my lab. So this is in data acquisition. So and so if you give power supply, so what I do, actually provide a very powerful power supply to so this data acquisition. So this make HBM. So this is very good 24-bit data acquisition system, 24-bit analog to digital conversion with, it's very high sampling rate, 19,000, which is obviously I don't need it at all. For the power supply or supplying the power to the sensor, so that data acquisition can do it, but I usually give this power supply from separately using a dedicated power supply. So so that is likely to improve your accuracy. And I have here also some arbitrary waveform generation facilities. So I'm not looking into it. So various. Okay, so this is a few slides here. I'm because I just discussed that the resonance. We have seen that the bridge collapsed due to resonance. Okay. Uh, So for resonance, uh, we need to understand the modal behavior, okay, or natural frequency in mode shapes. Uh, the natural frequency, uh, uh, it is not probably known to us at this level, okay. Uh, so here we're considering one single degrees of freedom system. Uh, so this is a so if we consider the free vibration is nothing but a uh, simple harmonic motion or a mass connected with a spring, but here additionally uh, with a despot means damping. Okay, so without damper, so a free vibration is oscillate for indefinite time, which is not real, which is mostly theoretical. Um, so here we have to consider the damping, which makes its behavior uh, like as you see around. Uh, so here, when you say give a induce a free vibration means just say unsettle the mass which is connected to a spring, say also a damper or despot. So and if we release it, then it start oscillating. Okay, in case of damping, it oscillate and suddenly reach to a still stand. And okay, and so this the oscillation, there is a frequency of oscillation. uh, so that is the natural frequency. I'm saying in terms of a single degrees of freedom system. uh, if it is a undamped, that is, though no damping matters, means only a simple harmonic motion and was connected with a spring, then its natural frequency is root over under root k by m. K is the stiffness, m is the mass. We know that it is very well known to all this as a physics student. Uh, so, but when we have a damp a damping is there. So damping is nothing but if you start an oscillation, then it comes to zero after some time. So that is the effect of the damping. Okay, so dissipation of, we also say in terms of energy is the for the is responsible for the energy dissipation. Okay, so as we naturally see around, if we have some oscillation, then after some time it come to a it stop after some time. Okay, uh, so for that the natural frequency is somewhat different. I'm not going to that in details. Okay, it's almost same. Okay, uh, yes, so we can see a single degrees of freedom system. Okay, mm, this is the spring, there is a despot means damper, and this is the equation of motion. Okay, and uh, it has a natural frequency. If we make some unsettle this mass from this rest position and leave it, so it start oscillating. Okay, and it has a, so that frequency is a natural frequency. uh, so this is almost equal to your undamped natural frequency. Okay, um, okay, very close, very close. Means for if it is made of steel, then it is around uh, almost 90 uh, 9 point say 98% same. Okay, um, so here we can see the a uh, in the right side we can see a a, a plot here actually. So what does it mean? Say you're exciting your that single degrees of freedom structure, okay, with some sinusoid excitation, okay, at different excitation frequencies, okay. Now say the natural frequency of this structure is, say it is a 2 hertz. Assume that natural frequency of the structure is 2 hertz, and suppose now you're exciting it with zero point 0.5 hertz, okay. And so so it is quite a way. It's a zero point 0.5 and 2 hertz is quite different. So you'll find your vibration level is smaller side, okay. And it will be same, suppose you're exciting with say 3 hertz, 4 hertz, then also you'll see this excitation intensity, or sorry, vibration response intensity of the single degree of freedom system mass is very not insignificant, okay. However, if you are very close to the natural frequency of this single degrees of freedom system, which is 2 hertz, you can see a significant level of vibration intensity, so which is resonance, and this also can show here in this plot, so which is representing in the y-axis, means the represent the your vibration intensity, x-axis it is uh, your excitation frequency. We are exciting in terms of a sinusoid force, all right. So this is the your uh, um, that resonance, and for the multi degrees of freedom system, so that we have seen for the single degree of freedom system. So for multi degrees of freedom system, here we get if we look at this free vibration, uh, so we have here the natural frequency and the mode shape, okay. So I'm assuming that you are aware of it since, okay, to some extent. Obviously this course is not can be finished in a very short time. I'm just giving an overall introduction. um, so for the multi degrees of freedom system, we have mass is not more a mass scalar, it is a mass matrix, stiffness matrix, damping matrix, and so here the free vibration is also there. So here the free vibration is mm, if you a problem uh, gives rise to a very special equation, okay, uh, which is our eigenvalue problem, okay. So uh, so this eigenvalue problem actually, uh, what is this? A multi degrees of freedom system has a multiple uh, mode of vibration, okay, and uh, so this is in the form a mode shape into, it is oscillating frequency under this sinusoid sine, say omega t, like this, all right. So but similar to similarly we have uh, your resonance, okay, frequencies, various modes, all right. And different modes are not the same, okay. Few modes are have more modal contribution, some are less, all right. uh, so for a multi-degree of freedom system, now the similar thing we can see, the multiple peaks here we can see here, okay. And Here, one very important term. So this is frequency response function. Okay. So many things in dynamics. So since this global level damage detection depends on the global signature like vibrations, all right. So uh, in dynamic analysis, frequency domain analysis is very important. So frequency domain analysis is not much new to us. Uh, mm, uh, so what we do actually, uh, a, a signal we can see as a uh, um, many sinusoids, okay, as a combination of many sinusoids and various frequencies, various contribution, okay. So anyhow, so frequency domain, mm, we need more some time in frequency domain, okay, uh, to develop expertise in this domain. And so in the frequency domain we can track the mm, this mm, those peaks, those natural frequencies, okay, we indicate as modes, okay. And if we look at here in this frequency domain, there is a very uh, convenient way of relating this excitation and this response. There is an equation in this slide. You can see that the there is a ratio of response and excitation. It is not function of time. Instead, it is a function of frequency. In the frequency domain, if we make this relation, we get a frequency response function. Okay, so this relation of input and output in frequency domain is so simple, just a multiplication. In the time domain, it is however not the same. In the time domain, the relation of this excitation and force is complex in terms of differential equation. All right. So in so we not only do all this testing, but in this for the last structure, we have some sort of constraint in excitation, because number one, it is difficult to excite, and secondly, uh, your excitation, we can't ensure that the response happened due to my excitation only, which is known to me, because winds are also uh, contributing to excitation of a large structure like a bridge. So it is difficult for excitation. It's not usual practice. Therefore, uh, so instead we can have techniques which are working fairly well. We call it operational model analysis, which based on the theories of random vibration, stochastic process, and a very fundamental assumption that the excitation is white noise. So that makes our theoretical developments very uh, help to develop the theories of operational model analysis, uh, which indeed doesn't depend on the knowledge of the excitation. We only measure the response. There is some prominent techniques for that. Against natural natural excitation technique with eigensystem realization algorithm, stochastic subspace. Many techniques are there. So there is some of the results I was in a team. It's maybe during PhD work. It's on a bridge we tested, and so we can do it. Now here, my just last, uh, I think 5 minutes, I'm discussing. So these are the most important part here. I like to mention here. Uh, so how to assess the location and extent of the damage. Uh, so we do it using the finite element. We have dependency on finite element model and its updating or calibration. So what it is actually, so finite element model, we know that it is an approximate. We can do a model uh, in multiple way. So um, now, um, so what you do here? So if to make a very reasonable way of modeling a finite element of a target structure, then what if we do? Um, um, we have to measure the its, as I said, natural frequency mode shape. This is a very important global signature of your structure. Okay, if you define your structure, and so if we have measurement, okay, measurement of natural frequency mode shape. So there may be multiple techniques. Even we do this directly measuring the vibration also. Okay, even we do it using impulse response. Even we do it using frequency response function. But uh, using uh, natural frequency mode shape is a very frequently used. And okay, I'm just discussing on it. And when we have a model, finite element model, and so uh, obviously from eigenanalysis we have is natural frequency mode shape, which is analytical. So it is obvious that it is not a exact match with your measured, experimentally measured uh, natural frequency mode shapes. So what we can do here actually, so to make our parameters value correct, we need some sort of optimization which will ensure a very good match between the your model natural frequency mode shape and the measured natural frequency mode shape. Obviously we'll tune our parameters like this so that the our model natural frequency mode shapes as much as match with the experimentally measured natural frequency and mode shapes. So we need some sort of parameters tuning. Okay, so what are the parameters? All right, so for this a is a shear frame, a very basic structure representing the most of the building. Okay, for its first mode, it may not be necessarily first mode, but in a 2D representation. Okay. Uh, mm, so mass may be a parameter, and stiffness. Say in most of the cases, we're very confident in measurement of or estimation of masses, but stiffness may not be that easy. So say stiffness, we can take a parameter, okay, and we have to minor adjustment in this stiffness parameters, or even if you consider other parameters, which will mm, which facilitate for a good match between the analytical and experimental measured natural frequency and mode shapes. So what are the major structural parameters? Young modulus, mass density, dimensions to some extent, uh, then spring stiffness, then composite parameters also very good choice, like flexural rigidity, then torsional rigidity, axial rigidity for truss. Okay, uh, and so that is the basic philosophy, and for that there are many techniques are there. So sensitivity method, a popular choice. uh, Bayesian methods are popular choice. Okay. Um, so to start with, sensitivity method is a very good choice. Okay. I'm just show you one paper which you can follow if you're interested to start with exercise with it. So there is some sort of exercises. So there are many you can see in these scientific publications. Many bridges are there in Taiwan. So since bridges are safety is paramount consideration, we can't actually accept any sort of disaster in bridge, isn't it? So bridges are a big concern. And in India also we're practicing. There is that Bogeybill Bridge, you know that. So there also a it is in target for a good health monitoring practice there. Uh, so thank you, and who are interested for that sensitivity method. So so that one you can start with. Yes. So the sensitivity method. So you'll get a many thing in this. You can start with. So thank you. So can
Thank you so much, sir. Thank you so much, sir.
yeah, thank you.
Thank you,
And
sir. Well, here, if you would allow, then I'll ask the participants to ask questions if they have any.
okay,
Yeah,
gotcha.
so participants, if you have any questions, you can ask by yourself, or if you'd want to put it in the chat box, then that is okay too. So I think we received one question in the beginning,
Yes,
and
yes,
that
yes.
is how SHM systems can be designed for us uncertainties arising from wind and earthquake loading.
Can you repeat, please?
The question is how SHM systems can be designed for uncertainties arising from wind and earthquake loading.
No, SHM is actually uh, uh, it comes after this design phase. Okay, so it comes after the design phase. So design and construction phase. So it is in operation stage. So uh, but there is some mm, uh, interaction is there. Say, uh, if we do structural health monitoring, then sometimes some information come out that say in a structure, say we can find that say in the second story some beam uh, showing damages. So structural health monitoring has ensured that. Now so that we can put a question to the designer that uh, it was designed well, then how we're say we're finding some sort of uh, uh, means not matching with the target of a designer. So then designer may do more introspect or more analysis. So in this way it is connected, it's not directly connected.
All right, sir. I hope the question has been answered for the participant. So that's all, sir. As we are not receiving any questions in the chat box, I think we can end the session, the first session of the day. Thank you
Yes.
so much for your presence here today.
Yeah, thank you, madam. Thank you, madam, very
Thank
much.
you, sir. Thank you
Yes.
so much, sir,
Yeah,
for your
Thank you, sir.
insightful session.
thank you.
So we'll start with the second session in a while. I request the participants to be with us until our second resource person joins us.
So, meanwhile, I can share the feedback link. I'm requesting all participants to please fill up this feedback. This is all about all the sessions. Since we have left with 2 sessions, so you can just wind up with this session, which is just now held. So I'm sharing the feedback link in the chat box. Participants are requested to fill up the feedback. Attendance link will also be shared. Please be patient. We'll be sharing the attendance link also.
A second resource person is joining by 3:45 p.m. So we'll resume then. Although please just do not disconnect from the meeting link.
Hello. Hello.
Yes, please.
Yes, what about the assessment test?
Assessment test, sir, will be held just after the third session.
So
And
at what time you're trying to stop? Thankful if you give me the valuable time.
yes, sir, we have already incorporated in the FDP schedule. So as per the schedule, we are conducting the test, sir.
So
So
is
it
it
is
online? So it will
yes.
be on the Atal website, no?
No, sir. The test will be in the chat box. We'll be sharing the Google form link. And we have already shared the feedback form. Please fill up. Feedback form is important.
Yes, but usually the test will be held on the Atal FDP website, no?
No, sir. The test will be held in here itself in the Google form.
No, but it's not possible. But it's not good. As per the rule, every assessment test will be held on the FDP Atal website. You have to upload the paper there.
Sir,
No,
as
but
we are,
as per rule, as per law, you can ask Dr. Sunil Luthra. As per the law, you have to upload the full paper on the website.
yeah, we are uploading that. We have already done that, uploading of the all full questions in the website.
Yes,
Right?
so we will open the link on the website because we have already registered there. We'll open the website and then we'll start the paper.
Just a minute, let me tell you, because in that case, it has happened that many of the participants are not attending, right? So in that case, everybody will fill up the form, which is like many of them are not attending right from the first day and they're filling up the form,
But they
which
will
we
not get certificate if they will not give the assessment on the at the FDP. They will not get certificate, madam. Certificate will be issued only when they will be
like that.
they
You
will.
attend the session also. So as per the guidelines, the AICT ATL guidelines, you have to attend the session and then only qualify for the test. And
That's
therefore,
correct.
that
Yes, yes.
reason we are doing it here in the chat box. We are sharing the link and you can appear in the test here itself. No problem at all. I
But
don't
how will I get certificate?
Certificate will be generated in the portal. Once we complete the marks, fill up all the marks there, then only your certificate will be generated.
That's correct. But if I
Sir,
will take the examination on the other website portal, then it is easy to get the certificate immediately.
no. Certificate not be released immediately. No, it's
No,
not like
immediately I have taken so many examinations. I'm giving the examinations since 2, 3, 4 years. I observed that once the examination is over, I will get the certificate.
No, sir. It's not like that. In AICT Atal portal, it is not.
Yes, and ICT, I have 7 certificates till now, madam. I have
Sir,
seen once
sir,
I
I
give the exam,
no,
once I will give the examination, I will get the certificate. I will
no,
first
sir.
I will fill the feedback form, then I will get the certificate.
No, sir. It's not like that. The
I have
form.
already given the feedback on the ICT Adult website.
No, that is good. That feedback is okay. But whatever we have shared, that is as per the AICT portal requirement. That is what we have shared with all the
That-
participants. And
That's
those who are
correct.
regularly only can be filled. Because if we share with everyone in the WhatsApp, you can see that the number of participants are 120, even more than that. If we will
Yes.
share the WhatsApp, then everybody will fill. We don't require for everyone. We will only require those are attending the sessions regularly, not for
We are
every.
attending regularly, but it's very difficult
All
for presenting the attendance on there.
Sir, I don't have any more further in this regard, since whatever
Okay.
we are doing as per the guidelines and as per
That's
the
right. Yes,
requirement.
yes. I appreciate your efforts. You are doing very good. And can you send me the PPTs of the USA people? When
We have
people have been.
shared the YouTube link, and whatever presentation we have received from the resource person, we all I keep sharing that in the WhatsApp group, right, sir?
And one
And
minute.
you will get all the presentation right from starting. The recording session recording is there from day one, so you can refer the session recording, and in the questionnaire also will be recorded the complete question for the for all the sessions, right, sir?
Yes, thank you. Can you share me the contact number of resource person of the USA person?
Sir, I will let you know. You will receive the certificate once we will physically verified each and everything in the portal, and that is
Okay.
from coordinator side can only be done, not from any
Okay.
other person. So
Yes, yes.
coordinator only, program coordinator means myself will be doing all the work in the portal, whatever
You are the
required
you
from
are,
your.
you are the coordinator, Sweta Burma, no?
Yes, right from the attendance marking to the marks also, the whatever marks you will be receiving in your test, that marks
Yes.
also I have to physically enter all the marks. Then only you will be eligible to get the certificate. And
Yes, yes. Congratulations, madam. You are doing very good.
that is
I want to
what I'm
congratulate
doing.
you. You
Yes,
have
sir.
done very good work. And you
It will
have
take
selected
time.
very good experts. You have selected very good experts from IIT level. It's very good.
Thank you so much, sir. Thank you
I
so
want to
much.
congratulate you for organizing the very good event. And
Certificate
we have
itself.
benefited from this. Thank you very much.
Thank you, sir. Thank you.
You can start the lecture, madam.
Good afternoon, sir.
Good afternoon, madam.
Sir, a very warm welcome. Sir,
Yes, thank you, madam. Thank you, thank you.
sir will be starting soon, sir. Just give me, sir, 2 minutes time because
Okay,
many.
okay, okay. I'll wait. I'll wait. No issues, madam. No issues, madam.
The participants are requested to look into the chat box and respond to the feedback form or the attendance. Meanwhile, I think we can keep on with the session, ma'am, technical session. I as a speaker join.
We
Yeah.
can start session.
Right. Yeah. So here it is. We are here with the second technical session of the day. Our second technical session is to be delivered by Dr. Leon Raj J. So give me a moment to introduce you to our participants. Dr. Leon Raj J is a principal scientist in the Applied Civil Engineering Group at CSIR NIST, Jorhat. He earned his PhD and completed postdoctoral research in structural engineering at IIT Madras after an ME in structural engineering from Alagappa Chettiar Government College of Engineering and Technology and a BE in civil engineering from St. Xavier's Catholic College of Engineering, both under Anna University. His work spans reinforced concrete deep beams, sandwich structures, pervious concrete strut anti modeling, and prefab earthquake resistant design, with publications across Elsevier, Springer, and MDPI outlets. He also contributes to structural health monitoring and sustainable materials, including alkali activated composites and climate resilient building initiatives. Beyond research, Dr. Leon Raj leads and support consultancy projects in testing, design, and non-destructive evaluation for public agencies and industry in the Northeast. He actively mentors students and shares research guidance through articles in the Hindu and the New Indian Express. Please join me in welcoming Dr. Leon Raj J to IFTP. Sir, I hand over the session to you.
Thank you, madam. Thank you for this wonderful opportunity. First of all, I thank the management for providing Royal Global University management for providing such wonderful opportunity to deliver the talk in the Atal AICT sponsored 6 days online faculty development program on seismic vulnerability assessment. And also I thank HOD madam for giving this platform for learning the faculties as well as students. Also it's a good platform for us to deliver the talk on the publications or research work we are carrying out. And then also I thank the organizers for making such wonderful platform to disseminate our knowledge. So this lecture will be on. I hope the slide is visible, right?
Yes, sir. Yes, sir. You can see your slide.
Okay. So the topic is on failure analysis of reinforced concrete structural elements. So structural elements means it's a wide topic. So instead of that, one of the structural element that is called reinforced concrete deep beams. So that's what I'm going to explain in this very specific topic, that vulnerability assessment. So introduction. So deep beams are the horizontal members loaded on one face and supported on the opposite face, so that the compression struts can develop between the loads and the supports. So this is the loading point. and this is the supporting point. Supporting point. Generally, deep beams are defined by when the span by depth ratio is less than or equal to 2, then it is called a deep beam. And when, as per IS 456/2000, when the span by effective span by depth ratio less than or 4, as per the ACI code definition, and this is as per IS code definition. So, according to ACI code, a region in between the loading and supporting points is the D region. So, as I said earlier, this is the loading point, and this is a supporting point. The region in between this loading and supporting points is called a D region. So, here in the first type of beams, you can able to see there is only one D region. Two D regions overlap with, while two D regions faces intersect, which is shown here. So sometimes two D regions, this is called loading discontinuity. So this portion is called loading discontinuity. So that means here there is no load, at this point there is no load, but here the load is applied, but here there is no load. So that means loading discontinuity is there. Geometric discontinuity means same depth. This kind of beams, for example, this kind of dapped end beams are called geometric discontinuity. Geometric discontinuous beams. So loading discontinuity means any point subjected to a point load. So here, when the beams are slender in nature, there will not be a overlapping in the D regions. When the beam reduces in between slender and deep beams, the D regions intersects. When in the case of if it is in the case of deep beams, D regions overlap. So in the first case, the length of the D region is equal to the depth of the beam. So that's called a deep beam. So while in the second case, the length of the D region is equal to 2 times the depth of the beam. So D means disturbed region. So this is disturbed region is 2 times the depth. So as I said earlier, L by D is equal to greater than or less than or equal to 4. That is the condition for ACI code. Further, B region appears between the D region and the B region. So what is in the B region? It's the region which obeys the Bernoulli's theorem. So that is called B region. So slender beams or Bernoulli's beams usually comes under this third category. So this is the tension reinforcement. This is the tie reinforcement or tension reinforcement. These are the struts. So you could able to see the strut formation here. Strut formation here. Then failure mechanism in bridges and high-rise buildings, foundations, offshore structures. Deep beams have successful applications like pile caps, corbels, and transfer girders, despite of complex load transfer mechanism. Why we are saying it complex load transfer mechanism? That we will see in the coming slides. There are multiple or combination of failure modes you could able to see. So if it is a tension if the bars are tested, then the mode is very simple or uniform. When the beam, like deep beam fails, it do not fails in flexure. It's a combination of flexure, flexural shear tension, diagonal tension, diagonal compression. So multiple failure modes and a combination of multiple failure modes. That's why we call it as complex load transfer mechanism. Failure of deep beams can cause a catastrophic collapse in the structural system. Various researchers concluded that the applied load on deep beams has transmitted to the supports through arch action, and the sudden release of stored energy in concrete indicates a brittleness of the shear failure. In normal beams, that's called slender beams, there is a truss action. In case of deep beams, it's arch action. So also the yielding of tension reinforcement and web reinforcements. So web reinforcements. So here we are giving web reinforcements. That means horizontal and vertical web reinforcement. Horizontal and vertical web reinforcement. Then crushing of concrete under diagonal compression failure, also anchorage failure. So these are the 5 types of failure possible in deep beams: yielding of tension reinforcement, yielding of horizontal and vertical web reinforcement, crushing of concrete, and also one more type of failure is anchorage failure. But anchorage failure, we avoid such failures because enough development lengths are provided. Then for beams with a low shear span to depth ratio, the stresses at the vertical web reinforcement were smaller than the yielding stresses of the tension reinforcement. Further, the longitudinal web reinforcement contributes to resisting horizontal forces of diagonal splitting force. What is into a diagonal splitting force? So this is a deep beam, and this is the supporting points, and this is the loading point, and this is the another support. So the crack appears like this, and this is the splitting force. This is a splitting force. The horizontal forces of diagonal splitting force, then sliding failure of the shear failure mechanism. So this is the sliding failure. Then flexural moments. The moments which is, so it leads to some kind of flexure, and flexural shear cracks also likely to appear. So these are the uh, parts where the longitudinal web reinforcement resists. Then size effect. What is the size effect? Kani's investigation showed that the shear strength of the RC deep beams did not increase with the deep depth of the beams. So what does it mean? So this is the shear stress. So shear stress equal to VU, applied shear force, divided by B into D, and this is the depth. If the depth is increased from say 400 mm to then 800 mm, if the depth is keep on increasing, the shear strength decreases. So this is what telling. This was told by Kani's investigation. Then subsequent experimental investigation of RC deep beams proved that existence of size effect. So this is nothing but a size effect. This is nothing but a size effect. The negligence of size effect resulted in overestimation of shear strength. So what will happen in this overestimation of deep beams? It leads to a catastrophic failure because the deep beams are the main parts of the buildings. For example, pile caps, then girders in bridges, then corbels. These are all the very important structural element in the buildings. So overestimating the shear strength leads to be a catastrophic failure. So methods to mitigate size effect may include proportionating the lengths of plates under loading and above supporting plates. Loading and above supporting plates under the loading. That means, okay, so under loading and above supporting plates. So that means a plate, the load should not be concentrated at a point, it should be distributed over a length. So that's what the point in this, we can able to reduce the size effect to some extent, then enhancing the strength of concrete, then distribution of web reinforcement. So distribution of web reinforcement, web means it is two, maybe horizontal and vertical, horizontal and vertical web reinforcement. So these are the two types of web reinforcement. So properly distributing, that is 0.25% or 0.3%, whatever it may be, the minimum reinforcement, or properly distributing with proper spacing can mitigate the size effect Then enhancing the shear strength also reduces the size effect. By distributing vertical web reinforcement both proportionating loading and bearing plates with respect to depth, the shear strength of the sanctioned trans beam showed negligent size effect. So you get able to reduce this size effect to some extent by proportionating the loading and bearing plates and also by distributing the vertical web reinforcement. On the other hand, strength alone does not govern the failure. Parameters such as transverse deflection and crack width. So transverse deflection and crack width is nothing but serviceability. So, of course, none of the structure is designed only for strength, also for serviceability. And nowadays, new parameters also there. We have to design for ductility and also we have to design for durability. All these things needs to be considered. But generally, being a structural engineer, you have to design a building for strength and serviceability. Serviceability means, importantly, you have to consider the deflection and crack width. Though experimental studies have been reported on the effect of web reinforcement on strength and serviceability, this present study describes the specific role of horizontal steel reinforcement in shear strength and failure modes of RC deep beams. Experimental plan to study the failure pattern. 3 sizes and 4 percentage of horizontal web reinforcement are chosen to study the effect of size and horizontal web reinforcement on deep beams. The effect of size and horizontal web reinforcement of deep beam is studied with 3 sizes and 4 different percentage of horizontal web reinforcement. The experimental results have been compared with other models. So models are proposed by the researchers and the models mentioned in the codes of practice. Codes of practice means it includes IS code, ACA code, Euro code, Astro code. So in addition, the strength reduction factor of maximum design shear force expression of deep beams mentioned in ACA 31814 and 31819 have been validated with the experimental results. Also, it is verified with the experiments whether the prescribed limit on maximum shear stress had been ensuring the yielding of web reinforcement prior to shear compression failure of concrete and excessive crack widths. So what does it mean? It is verified with the experiments whether the prescribed limit. So prescribed limit means the ACI 31814 and ACI 31819 have limited the shear force to a certain extent. What does it ensure? It is ensuring the yielding of web reinforcement prior to shear compression failure. Not only tension failure leads to yielding of tension reinforcement, there is also a yielding of web reinforcement. But in experimental, we find very little amount of strain in the web reinforcement. So still, it remains a complex phenomenon. It needs to be further studied with more experiments to explain these concepts. So effect of horizontal web reinforcement. For deep beams with the low shear span to depth ratio, that is nothing but LBD ratio less than 1, the horizontal web reinforcement was more effective against diagonal shear than vertical web reinforcement, more effective against diagonal shear. So in view of this fact, ACI 31819 and the earlier codes, so you can see 1995 and the earlier codes had recommended the higher quantity of minimum web reinforcement in the horizontal direction, that is 0.002, that is 0.25 percentage of the web reinforcement, than the direction, that is 0.15 percentage of the vertical web reinforcement. So later, ACA 318 minimum web reinforcement quantities were interchanged as 0.15 and 0.25. Again, in 2008, they are interchanging these values. In 1995, ACA code presumes that horizontal web reinforcement is important, but in 2008, the same code interchanged its decision to change the horizontal web reinforcement minimum criteria as 0.15% and vertical web reinforcement as 0.25%. That means vertical web reinforcement is more effective than the horizontal web reinforcement. So that was the presumption. Further, the quantities were revised in ACI 318 2011. It is in 2011. Again, they have changed and they have provided equal amount of horizontal and vertical reinforcement, that is 0.25% as a minimum web reinforcement in the horizontal and vertical direction to control the crack growth and crack width respectively. The beams were manufactured using the concrete mixture ratio of 1:1.8:3.1 and water cement ratio is equal to 0.4. And cement content is 350 kilogram per meter cube. So whenever you are citing the mixed proportion, always it is necessary to mention the cement content. So it is nothing but 350 in the 1.18. So 350 into 1.18 is equal to 413 kilogram per meter cube. So likewise, coarse aggregate is also same, and the water cement ratio is also 0.4. The average of 3 cubes was taken as the average of 3 cubes was taken as the mean strength of the sample, and the variation was maintained not more than plus or minus 15%. To obtain the stress strain response of the concrete, a core cylinder of 95 mm diameter was tested under a displacement control system corresponding to 600 mm deep beams with 0.3% of horizontal web reinforcement. The height to diameter ratio of the concrete core was 1.60. That means L/D ratio is 1.60. So the results are shown here. The stress strain response of core cylinder of the beam specimen BC 0.35H 600 is shown here. The axial strain and circumferential strain both are mentioned here. That means stress strain curve of concrete. This is the stress strain curve of concrete, and this is a stress strain curve of steel. Being a structural engineer, when you do experiments, first and foremost thing is to get the material properties. What is in a material properties? Stress strain response. Getting the stress strain response of a material, whatever it may be a bamboo, it may be as aluminium, it may be glass. So very important thing is this stress strain response. Wood, whatever it may be, you have to get this value, and the corresponding tensile strain is 0.0001. This is your corresponding yield strain, and corresponding uh, uh, so in the stress strain curve, the above mentioned beams concrete, the important observations were maximum compressive strain is 0.0015 and the maximum circumferential strain is 0.001 and the point of inflection is 0.0054. The Young's modulus and Poisson's ratio were 30.17 GPa and 0.13 respectively, similar to the stress strain responses reported by Narimon's literature. The ascending portion of the curve is linearly varying, so you can able to see the response is linearly varying. Subsequently, the response decreased asymptotically after the ultimate stress. A long tail of the curve was typical characteristics of the displacement control testing. So here you could able to see a long tail. So this could able to achieve because of the, this is called long tail. Here also you could able to see the long tail. So this long tail could able to achieve with the help of this displacement controlled testing. The characteristics of TMT bars were typical high yield strength and adequate elongation. In the stress strain response of bars, the trend beyond the yield point was non-linear. Beyond the yield point, so somewhere it is here, this is the yield point. So some beyond this, it's non-linear. So up to a point, you could able to see a linear trend. Then beyond this yield point, you could able to see a non-linear trend. Then loads corresponding to the initiation of the strain hardening and strain softening and fracture stresses can be obtained from these stress strain responses. So here, this is up to from this portion to this portion is strain hardening region. This is strain hardening region. And this remaining portion is called strain softening region. Softening region. So as the failure was brittle, the stress strain response gradually dropped beyond the ultimate stress until the strain softening and it fell down instantaneously when the bar is cut off. So here you could able to see at exactly at this point the bar has cut off and the stress strain response has drastically fall down. So type of reinforcement, we have provided two types of reinforcement. One is shear, another one is flexure. So for shear, we have used a constant diameter 8 mm bars, and for flexure, we have used two diameter 16 and 20 mm bars. So yield strength observed was in between 540 to 582. Then ultimate strength was observed between 646 to 689. Percentage of elongation was quite constant for the tested bars. The effect of horizontal web reinforcement on other international courts. So, okay, other international codes such as Canadian standard, Indian standard also recommend the minimum web reinforcement to control the diagonal cracking. As per IS 456-2000, the minimum ratio of web reinforcement to gross concrete area shall not be less than 0.002. That means 0.12%. The vertical direction in the vertical direction shall not be less than this is for horizontal direction and that is for vertical direction. So similar to earlier ACI codes, IS similar to ACI codes and IS 456-2000 had considered the horizontal reinforcement bars to be effective in resisting the RC deep beams. So here the horizontal web reinforcement is effective and it is presumed by IS 456-2000, and that's why it is fixed as 0.2% and vertical reinforcement is fixed as 0.12%. However, the Canadian standard recommends 0.2% equal on the both directions. The purpose of horizontal web reinforcement is not clearly described in the codes of practice. In particular, no information about whether minimum reinforcement is proposed for strength or serviceability. For what reason minimum reinforcement was proposed? Whether to enhance the strength or to mitigate the or deflection and crack width. So for what purpose the horizontal web reinforcement or minimum web reinforcement was provided? Bircher et al. Concluded the studies on large size beams and they recommend 0.3% as minimum web reinforcement. However, the different national codes of practice, non-uniformity prevails about the uniform amount of horizontal web reinforcement in the transverse girders. Details of test specimens. So 11 reinforced concrete deep beams were cast and categorized into three groups: D300, D600, and D1250 beam series. The variables of this study included the height of the beams varied from 300 to 1250 mm. Horizontal web reinforcement varied from 0 to 0.45%, and the width of the both loading and bearing plates varied from 100 to 400 mm. So these are the three series: D300, D600, and D1250 series. So here the only variable is the depth, the two variables, depth and percentage of horizontal web reinforcement. BC is nothing but deep beam of conventional type, and this 0.25 is nothing but percentage of horizontal web reinforcement. 300, 600, and 1250 is nothing but the depth of the beam. 0, 0.25, 0.35, 0.45 is the percentage of horizontal vertical web reinforcement. And the length of the loading and loading and bearing plates also proportionately varied according to the length of the beams. So then the compressive strength of the concrete, that is the target mean strength, were listed between 38 to 40 MPa. Then FCK is nothing but 33, around in and around 31 to 33 MPa. So you can simply say M30 grade of concrete. Say length of the beams were 750 mm and 1500 mm and 3000 mm, excluding the projections. Including the projections beyond the loading and supporting points. Breadth of the beam is constant, 150 mm. Depth of the beam varies from 300 to 1250 mm. Then percentage of tension reinforcement and percentage of horizontal web reinforcement. The percentage of tension reinforcement is kept constant, and this is percentage of vertical web reinforcement, and that is also kept constant. So this is this is horizontal web reinforcement only, and this is the vertical web reinforcement, which is kept constant. A by D ratio is constant, L by D ratio is constant. So these are the details about the beam designations which we tested for the failure analysis. Figure provides a reinforcement cage. 300 deep beams with 0 and 0.25% of horizontal web reinforcement were identical. Only one beam was cast. So that's why there is only 3 beams. So here the 0% and 0.25%, the reinforcement configuration is same. That is why we have cast only one beam. So here you can see and this is a loading point, loading plate. This is a supporting point, supporting points, and this is the loading point. And this is a tension reinforcement. This is vertical web reinforcement. And this is vertical web reinforcement. So when the beam size reaches a depth of 600 mm, we have to provide additional hooks to avoid bulging. For 300 mm size beams, we have provided 2 numbers of 20 mm diameter bars, and here we have provided 4 numbers of 20 mm diameters for D600 series. So only one vertical web reinforcement, because the vertical web reinforcement is kept constant as 0.33%. Only the horizontal web reinforcement is varied. In the horizontal web reinforcement percentage is also, the diameter of the bar is constant. Diameter of the bar is constant as 8 mm, and the remaining spacing of the horizontal web reinforcement is kept varied from 0 to say 150, 190, and 232 mm. 232 or 270 mm is the correct number of spacing. For D1250 series, the loading plate, the length of the loading plate was increased when compared to the D600 series. So here you can see 4 into 2, 8 numbers of 20 mm diameter bars, 8 numbers of 20 mm diameter bars, and 1 number of 16 mm diameter bars. And here the horizontal web reinforcement 8 mm diameter bars, whereas 2 bars of 2 numbers of 8 mm diameter bars. Vertical web reinforcement is also same. So vertical web reinforcement is also 2 numbers of 8 mm diameter bar, 8 mm diameter bar at 200 mm spacing, center to center spacing. So this is the representing mechanism, representing style, and this is at 3 different spacing. One is 0, another one is 150, another one is 190, another one is 270 mm spacing. Center to center spacing. So this is how it is represented. So loading plate, I explained everything about loading plate, uh, um, supporting plates, and here you can see the hooks to avoid bulging hooks. So lifting hooks also needs to be placed at appropriate places for lifting the specimen, and then enough development length. So this is the development length. So enough development length needs to be provided. Enough development length needs to be provided to achieve or to avoid the anchorage failure. So here this is a tension reinforcement. Then 4 beams are named after the size, that is depth of the beam, and percentage of horizontal web reinforcement. So instrumentation and test setup. I request the participant, please, the host, please check that there is a scratches in the shared screen.
Yes, yes, sir. Jay, I would request Jay to please, you please see now how to control it. Jay, are you here?
Yeah, fine. All the beams had been tested up to failure and under a 3-point bending test in a load control system under a hydraulic jack of capacity 6000 kilonewton loading frame. So this is nothing but a loading frame. Loading frame. This is nothing but the loading frame, and here this is a reaction. Reaction. Say this is a loading point. This is a loading point, and here you can see the supporting points. And the LVDTs were placed to measure the diagonal deformation. So this is so here the load is applied in this direction, and that's why this is called diagonal tension. Diagonal tension, and the other direction is nothing but diagonal compression. So diagonal tension, diagonal compression are monitored through these LVDTs. Then diagonal tension. So as I said earlier, when the load is applied in this direction, there will be a diagonal splitting, will be in this direction. To monitor this diagonal splitting, these 3 LVDTs are placed to measure the diagonal deformation. Diagonal deformation. Figure shows a typical test setup of D1250. So D1250 beam series, while placing the beams over the bearing plates with a minimum a mini laser projector was used to calibrate the adjust the loading positions. Actually, this line of action and this center line should align. So there is a laser projector was used to measure this to align this thing, and lateral supports were provided to avoid tilting in the other direction. So additionally, both the vertical and horizontal alignments with respect to the center of the loading frame were checked to avoid unintended eccentricity. So these all arrangements are made to to mitigate the eccentricity. The same length of the loading and bearing supporting plates were provided to prevent the instability and premature failure of the supports. So enough loading plates and supporting points will avoid or restrict the premature failure. In figure, the locations where the lateral deformations. Also, in addition to that, we have measured the lateral deformation. Lateral deformation means bulging in the other direction. So, for a beam, this direction is longitudinal direction, and this direction is transverse direction, and the other direction is lateral direction. So, this direction and this direction, if there is any bulging is there or not, is monitored through the LVDTs placed at the locations T, B, M. T means top, B means bottom, M means middle. So at these three locations, LVDTs are placed on the lateral directions to monitor the bulging of the deep beams. So this is the T place, and this is a typical figure, and B, and this is the M, where the LVDTs were placed in the opposite directions to monitor the bulging. So is there any bulging like this, and like this? Is there any bulging is there or not is checked with this LVDTs. The diagonal deformation and diagonal tension and diagonal compression were monitored using these LVDTs. Strut deformation. Actually, strut will form like this, and like this. It strut cracks appears like this. So these strut deformations are monitored these three LVDTs. There are two phases, phase 1 and phase 2. So on the phase 1 we have LVDTs, and on the phase 2 we have also LVDTs to measure the lateral deflection. So this is the loading point, and this is a supporting point. This is the loading point, and this is a reaction block. This is a spread beam. Spread beam means uh, the load is spreaded to 2 points. So here the load is applied at 1 point, and it is spreaded to 2 points. That is called spreader beam. So this is a failure modes of the failure modes and track pattern. So here the deep beams, you can see the beams of size 300 mm. You can see the anchorage failure. So enough anchorage we could not able to provide, so that you could able to see some kind of anchorage failure. And when the percentage of horizontal web reinforcement increases from 0% to 0.45%, that mode of failure changes from shear compression to diagonal compression. That is diagonal tension to shear compression. So here you can able to see there is no spalling of concrete when compared to this. Here you can see spalling of concrete. So these two beams you can see the spalling of concrete, and here you can see. So these two beams predominantly fails in diagonal tension. Diagonal tension. Diagonal tension, and these two beams predominantly fail in shear compression. So what is the reason? When the percentage of horizontal web reinforcement increased beyond 0.25%, actually, and this is beyond 0.25%, and it exceeds beyond 0.35, 0.25%, the mode of failure turns to shear compression. So which is further evident in the next D1250 series deep beams. So here you can see the beams without horizontal web reinforcement, the mode of failure. Here you can see the mode of failure. At the same time, the beams with higher amount of horizontal web reinforcement, the mode of failure drastically changes from diagonal tension to tension to shear compression failure. So the crack pattern of deep beams are shown here. Here you can able to see the loading points, and here you can see the supporting points. The crack width, that means the strut, could able to form at an angle of 56 degree, 59 degrees, and 56 degrees for D300 beams, and for 55 degree, 56 degree, 54 degree, 52 degree, and 54 degree for D600 series. So almost the diagonal, the angle of the strut is can be idealized as um, that means alpha theta equal to tan inverse of d by a. So that's what is shown here, and the other the width of the struts were measured in D 600 series were ranges from 168 mm, 170 mm. Then here you can see the diagonal compression failure on around 262 mm for the beams of provided with a higher amount of tension reinforcement. So here also the width of the struts was initially around the 446 mm and 470 mm. In the case of shear compression failure, it ranges to 400 mm and 498 mm. So wider the struts. So concrete predominantly fails in case of and the percentage of horizontal reinforcement. So you can able to analog this with over reinforcement concepts. So load versus deflection response. So here the dimensionless load, that means Vn is shear force, 2 into Vn is the applied load, B is breadth, D is the depth, FCK is the compressive strength. So 2 Vn test by BD FCK, that is dimensionless shear stress divided by compressive strength of the concrete. So it becomes dimensionless. Dimensionless deflection versus dimensionless strength versus dimensionless deflection were plotted here. So we could able to see the load deflection response of all the 11 beams are shown here, which grouped into the according to the percentage of horizontal web reinforcement. Here it is 0 percentage of horizontal reinforcement, 0. Here you provide 0.25%. Here you provide 0.35 percentage, and here you provide 0.45 percentage of horizontal web reinforcement. So here the maximum measured settlement at supports were in and around 0.01, 0.09, 0.05 mm for. So it's merely negligible. So we have measured the support settlement, but it is merely or ideally it is negligible. In the ascending region of the load deflection response. So this is the ascending region. From this point to this point is the ascending region. Ascending region of the load deflection response. The tensile strength of both flexural and web reinforcement contributed to the strength and stiffness of the beams. What is in the strength? What is in the deflection? Strength is nothing but the ability to bear the load, and stiffness is the ability to resist the load, resist the deflection. So this is the strength and the stiffness of the load. Following that, the yielding of web reinforcement, instability of concrete stress, and crushing failure of nodal region were responsible for the nonlinear low deflection response up to ultimate load, and the response gradually dropped down and the formation of the major cracks. So beyond this point, so there is the low deflection response drastically reduces, and a non-linear response has been observed. While testing, the peak point of the response of the large size beams has been reached much earlier than the both medium and small size beams, which shows the existence of size effect. So you could able to see here, this is the large size beams, and you could able to see here, this is a D600 series beams, and this is D 300 series beams, and this is D1250 series. So this beam, the height is less than the other beams, so it shows the size. There is the existence of size effect. So here you can see the difference. So it clearly shows the existence of size effect. As the failure of deep beams in D1250 series was both catastrophic in nature and full scale in size, the post peak regime has not been recorded completely. The LVDT is connected with the data logger, and as they were moved away. So in all the four beams of D600 series, complete pre and post peak load span deflection response were obtained. Additionally, the specimens of D600 series with 0% and 0.25% of horizontal web reinforcement exhibited a steeper gradient than those of beams with 0.35 and 0.45% in the post-peak regime of load deflection curves. The post-peak response of medium-sized beams with 0.24% to 5% of horizontal web reinforcement has been observed to be steeper than the smaller size beams with same reinforcement configuration. So load deflection response further, the peak values of dimensionless deflection and dimensionless shear strength were within 0.005 to 0.01 and 0.22 to 0.33 respectively for the beams with the 0.25% um, uh, and larger size beams. The comparison of delta by D values shown that the beams provided with 0.35% and 0.45% of horizontal reinforcement did not allow beams to deflect like beams with horizontal web reinforcement of 0.25 and 0.0% of horizontal web reinforcement. So dimensionless deflection of beams decreased at the depth of as the depth of the beam increased. Then transverse and axial deformation of strut. So this is called a transverse deformation. Then at the ultimate loads of D600 series. So this only we are showing about D600 series. So here you can see a sharp change of the deformation you can see. So at a strain of 0.001. So here earlier we have seen the material characteristics. When the strain reached 0.0001, the concrete starts cracking. So that is proved in this concept here. Here, this is the strain of 0.0001. So once the strain reached this limit, the whole event starts cracking. So a sharp point of inflection was noticed. So point of inflection, this is nothing but the point of inflection. Point of inflection. When the diagonal compressive strain reached the value of uniaxial compressive strain of 0.0005, the compression strut also failed actually. So these are the two strains. These two values we obtained from the material characteristic. So in the beginning of the lecture, I have emphasized the importance of material characteristics like testing of concrete, testing of steel, why it is important. So here we could able to see the importance of we can able to extrapolate the material behavior to the structural behavior. In general, out of plane deformation of the beams critical in shear is neglected. So usually that is deep beam, shear critical, shear walls, all these things are you can see you could not able to see any out of plane deformation, but still we have measured it. So but the conclusion is that it is within the proposed limits. So this is the deformation. You can able to see a 2 mm deformation, and this side also 2 mm deformation. So here you can see less than 1 mm deformation, and here you will see less than 2 mm deformation. So in and around it is less than 5 mm. So we can ignore this out of plane deformation. So Zhang and Tan also observed, and they have obtained a maximum out of plane deformation as 0.15 mm, and we have observed a maximum out of plane deformation as 7 mm, 0.7 mm. So it's fine. We can ignore it. So further studies are essential to introduce a limit on the depth to width ratio. So it has an impact on the lateral deformation. That D by B ratio has an effect on this out of plane deformation, that is bulging and buckling effects of the strut. Then strength results in all the three series, beams provided with 0.25 percentage exhibited the reserve strength index in the range of 171 to 200%. Then deep beams with the D300, D600 showed an incremental strength of 83 to 171, 153 to 197, and 102 to 200% of the initial cracking strength. So in VCR is nothing but initial cracking strength. Then VN is nothing but ultimate strength. This is shear stress. Then failure mode, DS is diagonal splitting, and S is shear compression. Then R is nothing but the reserve strength index, the ratio of difference of the cracking minus ultimate load divided by cracking load is nothing but reserve strength index. Delta SCR means serviceable deflection, and ultimate deflection, and collapse load deflection. So for tests with beams of average strength index was 148% of cracking strength, and load from ultimate load of 59% actually. So here you can able to see the ultimate loads. Also the applied load is nothing but 2 times the shear force, is nothing but the applied load. So depth effects of deep beams for initial cracking load. These are all nothing but the initial cracking load. So a similar work was done by Rao and Prasad, where you could able to see the initial cracking load. You do not find a or mitigable or negligible size effect. But at the same time, the large size beams have showed a significant size effect. When the depth increases from 250 to 1250 mm, the strength decreases. So this is nothing but this is a dimensionless shear strength versus overall depth, and this is nothing but the size effect. So this strength results again confirms the existence of the size effect. In addition, the strength variations of the high strength concrete deep beams are attributed with the same geometry of 0.2 and 0.3%. Horizontal shear reinforcement are also shown in figure, that previous figure I have shown here. Though Rao and Prasad beams of were high strength concrete deep beam, the shear strength decreased in the range of 35 to 55%. So here you could able to see this is Rao and Prasad's beam. So, but whereas the proportionated loading and bearing plates is so negligible, or the size effect is mitigated. So here the strength you could able to see that trend. So instead of very steep strength, we could able to see a mild or mitigated size effect. So 15 to 38%, whereas the Rao's and Prasad's beams showed 33 to 55%. So it is observed that the range of the strength loss was say 11 to 20% when compared to D300 beams with D1250 beams. Large size beams made normal strength concrete were performing better than high strength concrete deep beams at the ultimate load. For experimental results, it is evident that size effect was significantly mitigated by proportionated loading and bearing plates. when the percentage of horizontal shear reinforcement increased from 0.25% to 0.45%, in beams of 300 series, the ultimate shear strength decreased up to 22%, and the initial cracking strength increased up to 16%. For D600 series, the ultimate strength increased from 23, 8, and 9% for beams endowed with 0.25, 0.35, and 0.45% of horizontal web reinforcement when compared to beams with horizontal web reinforcement. Then further, in D1250 series of deep beams, increase in initial cracking strength were 3%, 6%, 16%, 18%, 8% for beams endowed with 0.25, 0.35, and 0.45% of horizontal web reinforcement when compared to beams without horizontal web reinforcement. Ultimate strength has increased to 23% for beams with 0.25% of web reinforcement with reference to the control beam. It seems that the initial cracking strength of deep beams increased with an increase in the quantity of the horizontal web reinforcement. Also, it is inferred from the results that ultimate strength of deep beams or optimum amount of the horizontal web reinforcement was 0.25%. So there are two reasons for strength loss in beams with the 0.35 and 0.45%. Relatively high quantity of horizontal web reinforcement, high yield strength of the web reinforcement, and horizontal web bars located very close to the tension reinforcement. So these are all the reasons for the reduction in the strength actually. The ratio of the predicted to experimental shear strength is defined as the strength ratio. The variation of strength ratios were calculated for Canadian standard, Stratton type provision of ACI code, maximum design shear force, ACI code 318 2014, 2008, Matamoros and Wong's model, Tang and Tan's model, Rizzo's model, Zhang's model, Rao and Sundaresan's model, Prostio's model, and ACI 319 were evaluated. Further, the aforesaid equations were briefly named as Matamoros, Tang, Rizzo, Zhang, Rao, and Prostius. So Prostius model and maximum shear strength expressions were empirical type, where none of that expressions was developed based on the cylindrical compressive strength of when the if the expressions were based on the cylindrical compressive strength, the equivalent cube strength was calculated as per SP 24 1983. Validation of strength results. So here you could able to see the IS code is predicting, it's underestimating the values, whereas the Canadian standard overestimates. Then Rizzo's model is predicting very close. Tank's model very close. Then Matamoros model very close. Zhang's model overestimating. ACI code without strength reduction factor. It underestimates most of the beams, overestimates most of the beams. ACI code with strength reduction factor predicts the beams of with yeah, predicts the beams within the range. So this is a safety line. So the code should predict the beams within the safety limits. So the strength reduction factor is good enough for ACA 2014. Then further, which one is good? 2008 equation or 2014 equation? As 14 equation is good for conservative point of view. So then Rao's model also predicted in a better way. Then Prostio's model completely underestimates the completely could able to mitigate the failure. Then ACI 318 2019 model with VN max slightly overestimates because it removes the strength reduction factor. So in the later code, in the recent code, the strength reduction factor has been introduced again. So limiting shear strength expression suggested by ACI 3119 is more conservative than any other models of ACI 318 2014 and 2018. Sorry, this is, I think, Stratton time model. This is the shear strength expression. So the strength reduction factor proposed in ACA 318-14 and ACA 318-19 seems to be adequate to prevent the shear compression failure of deep beams, and the design limit expression accounted for only 66 to 61% of the average experimental strength respectively. So shear strength expressions proposed by IS code. So this is nothing but the Fy, AST and Z. Z is nothing but the lever arm. The lever arm is given by these expressions. Then Matamoros model, it is purely an empirical model. So where it is a function of concrete contribution, then vertical web reinforcement and horizontal web reinforcement. That is VC, VH, and VV. So in this contributions, in this model it has been made. Then CSA model, that is Canadian Standard Model. So it is based on the Stratton type model. So this is A1, A2, A1, B1, AD, A2, B2. So all these things are the capacity of nodes, struts, and struts, tie, and the nodes. So here, once all these things are calculated, minimum of the node capacity, strut capacity, and tie capacity. So strut, tie, strut, tie, and node. So this minimum of these three shall be the um, capacity of the deep beams. So Tank's model is also based on the same formula, that capacity of steel, the shear reinforcement plus the capacity of concrete actually. So Rousseau's model is purely an empirical model that is also based on the concrete contribution of concrete, VC, contribution of vertical web reinforcement, horizontal web reinforcement, and contribution of vertical web reinforcement. So Xi is a strength reduction factor they have introduced in the VC. This is the famous Zhang's model. So it's quite complicated, but it is very good in prediction, and it could able to see the. It is also a function of concrete contribution plus shear reinforcement. So additional efficiency factor and strata efficiency factor and boundary conditions were applied for the proposed struts. Then ACA Stratton time model 318-14. So here Stratton time model, here the minimum of the strut, tie, and node capacity is the capacity of the Stratton time model. ACA 318 maximum shear strength expressions are very simple. 0.83 square root of f dash of C B in D, and ACA 318 2014, the expressions are 0.83 square root of f dash of C B in D. So this is the strength reduction factors. So those who are doing PhD, so they can able to like this simple expressions can also be modified. So you need not go for a bigger level of complicated equations. So the beauty lies in the simplicity. So if the equation is very simple and your equation will be your equation will be utilized, or it will be cited by many people. So then Rao's model. So the Rao's model is also based on the size effect and the concrete contribution VC plus VH and VV. That is contribution of vertical web reinforcement, horizontal web reinforcement, and shear reinforcement. So Prostro's model is 0.25 dash of C into BD. This is very simple model. It needs further modification. Then ACA 318 2019, they have introduced one more modification factor for the normal and lightweight concrete. So this is almost 5.75. That is a size effect factor has been introduced. That also predicts quite good. So when compared to the various models, IS code, Matamoros model, Canadian standard, Tang, Rousseau, Zhang, ACA code, STM, Stratton time model of ACA code, ACA code's maximum shear strength expression, Rao's model, Prost's Prostos model and ACI code, you could able to see the mean, standard deviation, and the coefficient of variation here. So the mean value should be in and around 1, and the standard deviation should be as minimum as possible, and the coefficient of variation should be also as minimum as possible. So out of that, if, the mean value which is very close to 1 is this is a tanks model. Then other than that, we could able to see the ACI 318, 2008, 2005, 2008 models. Then you could able to see 0.99 Rouse model is very good. Then here you can see the standard deviation also 16% and coefficient of variation also 16%. So it's quite a good model. Which lowest coefficient of variation is good, but here you can IS code you could able to see the mean value is 0.43, which is very less, but the standard deviation is quite good. So this IS code needs a certain kind of some enhancement factor to predict in a decent way. Then serviceability results. So here, serviceability failure is considered to occur when the specified limit of deflection and crack width is exceeded. The service load was the applied load on the beam when the crack width limit is reaches 0.3 mm. Ultimate and collapse loads were the loads corresponding to the maximum applied load and the maximum post deformation of beams. As per IS 456/2000, the limitation imposed on the span to deflection ratio, including the effects of temperature, creep, and shrinkage after completion of horizontal members and erection of partition, should be greater than 250 and 250 respectively. It is observed that the span to deflection ratios decreased with an increase in the load levels. The average service load, ultimate load, collapse loads were 2.7, 7.2, 9.4, and 38% respectively. At service load corresponding to crack width limit, almost all the beams passed deflection criteria and span to deflection limit. As the horizontal web reinforcement close to the tension reinforcement contributed to the moment of resistance, beams reinforced with 0.35 and 0.45% of horizontal web reinforcement exhibited both relatively high stiffness and reduced deflections at the ultimate load level. So crack width, as per Indian standard, crack width limits are 0.3 mm for non-serious cracking, 0.2 mm for structural member tension that is continuously susceptible to wetness, 0.1 mm for elements or aggressive environment. For example, water tank, the serviceability limit is very low. Because to avoid the leakage, in D600 series, deep beams reinforced with 0.2, 0.25, 0.35, 0.54% of horizontal web reinforcement reached the crack width of 0.4 mm, 56, 70, 92, and 80% of ultimate load respectively. The percentage of applied load reached the crack width limit of 0.3 mm. It is evident that a relatively high quantity of horizontal shear reinforcement significantly has restrained the diagonal crack width and increased the service load. The measured crack width had exceeded the limit if the mode of failure of the beam was due to diagonal splitting. From the crack width analysis, it has been understood that the failure maturity of large size beams is faster than the small size beams. So this is the crack pattern as the applied load. You can see applied load is nothing but the total applied load divided by the corresponding load. We could able to see the crack pattern. See the 0.2 0.2%, 0.2 mm. So those who are doing PhD, so you can bring these concepts. Most of the students, they concentrate only on the strength only. So you have to have the deflection also. You have to see, and the percentage of service load. This is nothing but service load, and this is 0.2 mm and 0.3 mm. This is 0.4 mm. This is 0.3 mm. And those could do consultancy services. If you are going for field visit and for observing the cracks, so you have to keep it in your mind that if the building is the crack width is beyond 0.3 mm, it fails in serviceability. And if the building cracks or structural cracks, then it needs repair or rehabilitation, or if needed, retrofitting. And there are mild differences between repair and rehabilitation. Repair works means according to the condition we have to increase the service just to solve locally. So it's called repair, and rehabilitation is nothing but uh, bringing back to the original service load condition. So here the service load condition. So for bringing back the bring back the structure to rehabilitation condition. So in that cases, these service load concepts are helpful. So retrofitting means enhancing the strength. So here you can see the crack patterns are growing like this, and then another crack is like this, and then another crack with this like this. So what does it mean? So it is very simple that when the crack width limit exceed 0.4 mm, the beam fails in the serviceability. So final conclusion, based on the shear strength and serviceability results of RC deep beams, 0.25% of horizontal reinforcement was found to be optimum for better performance. Size effect was mitigated to a strength loss of 15 to 38%. By increasing the percentage of horizontal web reinforcement from 0 to 0.45%, the failure mode changed the diagonal tension to shear compression, and the failure strains of strut in axial and transverse strains were 0.01, 0.0001 and 0.0015 respectively. The span to deflection ratio decreased with an increased applied load. That is obvious. When the large and medium sized beams had failed in serviceability criteria of crack width at constant load, small size beams were early stages of cracking due to the size effect. So size effect has a significant role in the structural design. So even if the failure mode was shear compression, the strength reduction factor of maximum shear strength expression for deep beams are given in ACA 31819 is adequate. So this was the conclusion. So with this, I conclude my session. Thank you.
Thank you, sir. As it is, we conduct the session, and then we also provide a platform for question and answers. I would request the participants to give their questions if they have any. And you can also write the questions in the chat box.
Nice informative session. Thank you very much. Thank you, sir. Thank you.
Usually we wait for a minute for
No issues, no issues. Take your time.
participants. Let's see, sir.
Yeah, wait. I'll wait. No issues.
Okay. Ma'am, would you like to add anything?
So thank you, sir. Thank you for enlightening us and our participants with your informative session. Thank you so much, sir.
Thank you, madam. Thank you very much. So we'll close here, madam.
Yes.
Yes.
I think we can go ahead. Yeah. Thank you so much for your insightful session, sir.
Thank you. Thank you.
Yeah. I request the participants to be there until we start with the next session. However, there is an announcement here that right after the third session, the final session, you will be provided half an hour, 30 minutes to go ahead with the test that is required for the certificate. So you will be provided that much time and you will have to attempt it, and then we will go ahead with the valedictory session with a concluding remark. Thank you. So
I
please.
think Arthur has already joined. We can straight away start the third session.
Sure, sure. Sure, ma'am. We'll start with our third speaker today. So here our third technical session of the day is to be delivered by Dr. Roman Babu Oinam. Dr. Roman Babu Oinam is an assistant professor in civil engineering at IIT Guwahati, specializing in seismic retrofitting, passive control systems, reinforced concrete and steel structures, fiber reinforced concrete, and hybrid simulation testing. He has previously served at IIT Tirupati and NIT Warangal. His research includes experimental and numerical studies on seismic strengthening, yielding damping devices, and retrofit strategies for non-ductile open ground story buildings. He has over 15 journal papers, 6 book chapters, and 28 conference publications, and has led several sponsored research and consultancy projects. Sir, we are truly delighted to have you here today, and I hand over the session to you.
Good evening, all. Hello, is it audible?
Yes, sir. You're audible.
Okay, the slide is in the
Sir, you are
presentation mode,
audible.
or-
Sir, you're audible, but the volume is little less.
So, sure. So what about now? Is it fine?
Yeah. Yes, sir.
Okay, now it's clear, right?
Yeah, it's clear.
Okay. So my PPT is in the presentation mode or slide mode or in the presentable mode? How is it look?
It's not covering the full screen. I think you have to go to the display settings and put it into the slideshow.
Okay.
So it's on the top. Display settings.
Okay, 1 second. Sharing. Display setting. What about
No,
now?
actually, so display settings was there. So first you have to go to the presentation mode. Yes, sir. Please click on that first.
Is it coming?
Yeah. Just I can't. Yeah. So now, sir, you can see on the top right or left. There's display settings in the middle. First is show taskbar, then there's display settings. Yeah.
Yeah.
Click on that. Yeah.
Duplicate, right?
Duplicate slideshow. Yeah. Yes.
Okay. So how is it now?
It's again come back to the PPT mode. Yeah, now it's.
Now is it clear?
Yes, sir. Full screen.
Full screen. So is it moving to the slides are moving or not? This is
yes, sir. It's moving. It's moving.
Okay. So shall we start?
Yes, sir.
Okay. Thank you. Thank you for Department of Civil Engineering, Royal Global University for this invitation. Okay, today I'll talk about this seismic evaluation retrofitting of non-ductile open ground story building using the yielding damping device. But I will not confine myself on not only the yielding damping device. I'll try to cover some other retrofitting strategy also. Okay. Now, before moving to our retrofitting and that strategy, first of all, let's try to understand one of the that disaster. We have a lots of different type of disaster like flood, wind, and cyclone and earthquake. So I'll focus only about on earthquake. Okay, so the earthquake mainly happen on due to this man-made earthquake and a natural-based earthquake. And when we talk about this natural-based earthquake, and that earthquake happened because of our tectonic plate movement. And I know that. So today my session is the last. In the last couple of days, many of the experts might have given a different topics, something related to this also. But for me, I'll try to cover up a kind of a summary for this earthquake as well as the application base. Okay, let's proceed. And whatever I mentioned, this earthquake, and especially from the Indian context, okay, what are those plate tectonic movements, and what is the major cause of this earthquake, especially on this eastern part of the India? Okay, so please have a look this short video. From here, we'll get clarity about uh, this video is. I think it's not playing. Okay, anyway, so this video is not playing, and I don't know why. Just few days back, a few days minute, few days it was playing, but here it's not working. But that same information I'll present with the help of this diagram. So this Indian continent is colliding with this Eurasian plate, and because of that, the Himalayan has formed that everybody knows. And as a result, this region is a highly seismic zone. And of course, the eastern part of the India is the end of this Himalayan part, and though so that's this region also is a quite proactive in the seismic activity. And if you look this the seismic activity, the Indian plate is kind of the just inserting below the Eurasian plate. As a result, here this one direct collision is happening. Okay, but in the eastern part of India is a collision as well as the segregation. That both mechanism is going on. That is much more complicated. And now because of that, different type of the earthquake is generated, and all of us knows that earthquake is a different wave. Okay, it's a body wave and surface wave and all. Now I'll show one another image here. uh, okay, this one. Okay, this image is from the Nepal earthquake in 2015. In that earthquake, uh, this okay, here again this video is not playing. So can I hold for some 10 seconds and I'll cross check it, because this video is working in my system, but the moment when I came to the Zoom, I think it's not playing. So can I hold for 10 seconds here?
Okay, sir. Okay, sir. Please.
Okay, I'll stop sharing and I'll just cross check it myself.
Sure, sir. Sure.
1 second. Yeah, actually that's all my whatever the previous video and everything. It is working in my system, but the moment when I present in the Zoom, and that is not working, and I don't know why. So
Sir,
let me try once again. Yes.
it is maybe because of the video. We again have to put it in a display setting. We have to check it. And sir, again, if you can click that mirroring, or it will come, sir.
Okay.
That duplicate.
Let me check. Let me check. Did you, did you see this slide mode, madam? Is it visible?
Yes, sir. Yes, I can see the
Okay.
slideshow. Sir, again, you have to do here from that display setting. You have to again.
1 second. So that full
Yes,
view is not.
yeah, it is moving. Yes, yes, sir.
Okay, fine. So I'll just explain. Okay, here if you this is the slide mode, right? Right now, how is it looks?
So it is a slide mode, but we can see the slide from the next also. I would request Jay. Jay, are you here?
Yes, I'm here. Let me help. Okay,
Guide us.
sir, can you click on the display settings option in the first?
Yeah.
Duplicate the slideshow, then come up. Let me just check.
The moment when I click the duplicate slideshow, this video is not working.
Just give me a moment.
So video, not only the video, all the animations are not working.
Okay, can you just like come out of the presentation mode and then let me see the screen? If possible.
Yeah, I remove the presentation mode now.
Okay. Um, when you share your screen, just check that if there is an option for entire screen sharing.
Okay, here entire screen sharing is there, both screen one and I have.
Please share the entire screen so that I can view your screen and guide you further.
So how is it?
Okay, yeah, it's come up. Now go to the presentation mode and then display settings, and then there is an option for duplicate the screen. I think it should work now. No, it's not
Screen sharing has stopped because of the external
There's
display.
some glitch.
So it is also a warning. Screen sharing has been stopped because of the external display disconnected.
Okay. So can you disconnect the extended screen and just present normally if possible? I think there is some error in the display settings, so that's why it's not working properly.
Okay, then otherwise I'll just leave the meeting and I'll present from my laptop. Let's see from that.
Okay, sure, sir.
Okay. Now, is it audible? Yeah, sorry for screen.
Yes, sir, you're audible now.
Yeah. So, can you see the my presentation?
Yes, sir, it's visible.
Yes, sir. Yes, sir.
Okay. One second. Ma'am, actually, that video is properly visible or not?
Yes, sir.
Okay, fine. So then in that video, whatever you observe, so that video is from the Nepal earthquake 2015. And if you look carefully that video, the middle part of this traffic island, the one this idol is here, and structure, the top, the surrounding structure is nothing got damaged. Okay, only that traffic island structure got damaged. And why it got damaged? Because in that traffic island, whatever the dome type structure, the entire mass is concentrated at the top. And if you look, all the support system, like especially the vertical member, they are quite flexible. Okay, that's how the structure got collapsed. And this typical mode of failure is known as a soft story mechanism failure. So that way, I'll just talk about today my overall this one retrofitting of this open ground story all. This is highly relevant video. That's why I shown here. At the same time, when we talk about this performance-based design, okay, and what type of damage is allowed in structure, the performance-based design, and also known as the earthquake resistance design philosophy that people are talking about. And the moment when people come to know, okay, earthquake resistance design means they think that the entire structure is going to resist the seismic activity. Okay, but concept is not that way. Okay, so now we allow damage in the structure. Okay, but what level of the damage allowed in the structure? That's the performance-based design. Okay, we have the different intensity earthquake, like minor level to the strong shaking level, and even in the minor level earthquake, so the cracks in the wall, okay, especially in the corner joints of this your here actually, especially in the wall corner or window corner, those area where your this one. Oh, why is showing it is. Yeah, so those cracks, especially from the corner of the wall and corner of the door, corner of the window, this is acceptable. And when you talk about this, uh, in case of the moderate level earthquake, the minor yielding in the beam is allowed. Okay, that you can see here. The minor yielding is allowed, but not in the column. But in the strong shaking earthquake, it is allowed to damage on the wall, beam, as well as the bottom column. Okay, but the collapse of the structure is not permitted. Okay, this is known as our earthquake resistance design philosophy. So means we should not think that earthquake resistance in the sense the entire earthquake seismic force is going to be resisted by the your structure. Okay, that concept is not that way. Now, if you look this structure regarding the earthquake, and let's try to understand the structural mechanism as well as your seismic activity. Okay, the different earthquake ground motion, how it's impact to the structure. And this the figure shows that this is from the Kobe earthquake 1995, and the overbridge, the entire your bridge pier is got collapsed. But if you look carefully, the superstructure is intact and not significantly damaged. At the same time, if you look here, this is another bridge. Okay, this second bridge, this is from the Loma Prieta earthquake 1999. Here, the vertical support, like the piers structures are okay, well and fine, but your superstructures are entirely disconnected. Okay, it was collapsed. But why these two different bridges are having a different type of development? Okay, that depend on your earthquake ground motion. As I mentioned in the beginning, you have the tectonic movement, and plus if your fault lines are very close, okay, then two type of the earthquake you can face it. Okay, near field earthquake and the far field earthquake. And in case of the near field earthquake, you have a permanent offset type damage. But in case of the far field earthquake, you will have the asymmetrical oscillation. So in the previous diagram which I shown, that is the purely a shear dominant type, and here all are kind of the vertical movement is strong, motion is quite strong. That's why your all the deck slabs are got collapsed here. So because before retrofitting itself, you need to understand what type of the earthquake are you expecting. Okay, most of that structural engineer who are working in the field of retrofitting, they always talk about your structural behavior, and you try to strengthen the structure. Okay, but sometimes we also need to understand what is the type of the earthquake we are expecting, especially in that zone, and accordingly we can take some measures on the retrofitting strategy. Okay, now again another a short video, please have a look. And in this video, what did you observe? This is another experimental, and it is known as our pounding effect. And the two structures are constructed, and both are in well and good condition. But if you look to the building structure, your slab zone, that is the quite rigid. Okay, and whatever the column portion, that is known as a flexible zone, and which we are staying in the room. Okay, whatever our available floor area, floor spacing, that is the one of the weakest zone. We are standing on a slab, and our roof also slab. Those are the kind of the quite rigid portion. But if you construct a two structure consecutively, and if they have a different height, one rigid portion, okay, here this is slab part, this rigid portion is keep hitting to the one another soft region. Okay, that's how the next building is got collapsed. Okay, such type of the failure pattern is known as a pounding effect. But so because they were wrong construction, even in the small scale intensity earthquake, and we also got damage in the structure. So in case of the retrofitting such stable structure, no need for doing any kind of the modification on the structure. If you have such things, you try to provide a clear spacing by removing the boundary portion. Okay, then you can set the structure. So that's how you can identify what are the different strategy. Okay, no need for modify your structural component. It's in everything. Now coming to this seismic activity in the past, and this is the data presented in the last 600 years. Okay, from the 15th century to this up to the 21st century. Okay, so 20th century, it's in every dot here, it represents one earthquake. Okay, so bigger size of the circle represent the higher intensity of the earthquake. The small circle represent the small intensity of the earthquake. Based on this data, past data, it's our seismic code was developed. Okay, currently our seismic code has a seismic zone 2 to 5. Okay, so if you look back in the 80s and 1980s and in the beginning, we have zone number 1 also. Okay, that zone 1 was merged in the zone number 2. That's why you can observe in the current seismic code, the zone is starting from 2, okay, up to 5. And enter this northeast region, okay, we are under seismic zone 5, and some portion of this Uttarakhand, Srinagar, Jammu and Kashmir, and some portion of the Gujarat, Bhuj, Kutch area, those are seismic zone 5 and quite critical, and including the entire Andaman and Nicobar also. But this is the another code which is under review, the same IS 1993. It was drafted in 2023. And if this code is implemented, entire northeast part and upper portion of the Bihar and this Uttarakhand and entire Jammu, all this portion will be under the seismic zone 6. Okay, right now we are in the seismic zone 5, but if this draft code is implemented, we will be under the seismic zone 6. Now, based on those seismic and seismic zone factor and the critical condition, we need to understand our challenges structure. Sometimes purposefully, because of our wrong construction practice, we also make some casualty during this seismic time. And among these irregularities, you can see the plan irregularities and your the elevation irregularities are there. Among these, like open ground story condition and this hill slope condition, those are quite common practice in our real day-to-day life. And how to take the precaution on those things that I'll discuss. But for the hill slope, I will not cover here. I'll focus only on open ground story. And so why those sub-story come in the picture, that you understand because of the missing of the masonry wall and all, that sub-story come in the picture. And including that masonry wall absence, and because of the poor quality construction in our real life, that also kind of increase the level of our vulnerability. Okay, so can you imagine this column? Whatever the reinforcement they use here, it's almost around 8 mm diameters used as a reinforcement bar. Okay, so which is not at all acceptable, and there is no that ductile detailing here. Such type of concrete is known as a non-ductile concrete. Okay, so now if your structure has this non-ductile category concrete and plus open ground condition, then the combination is very drastic combination, is a very critical. And you can observe here, this is the kind of the slabs are just folded like a bread. Okay, so the such type of failure will be observed. One thing you can observe in the this Bhuj earthquake, a similar kind of the failure it has already occurred. Now, seismic demand and the requirement, that let's have a discussion. As I mentioned, that depend on your seismic condition and all, you need to understand the structural behavior, and plus, especially for your existing structure, when it was constructed, and currently what is the condition of the structure, that also need to be. And before moving to your physical verification, theoretically you can check some of your the vulnerability on the structure. Whatever I have shown here, this is a one particular example. Okay, so this building was constructed in the 80 series. Okay, and the mass of this is a G+3 story building, and total mass is shown here. And based on this available this information, okay, the building was designed as per the IS 1983 1962. Total base shear is 230 kilonewton. Okay, this 230 kilonewton this demand, the building got designed, and still that structure is standing. Okay, as per the current code, if you re-evaluate that building, the requirement is 851 kilonewton. Okay, huge gap. It's a 3.7 times required. Okay, currently you design for this, but actual requirement is the 851. So it means by default, the retrofitting is required for such type of structure. And you can find such type of the n number of the structure, especially in this metropolitan cities like Delhi, Kolkata, and all, because during the 60 series, the huge mass construction was carried out in those cities. Okay, so now after understanding all those things, and first of all, you need to identify it. Okay, what type of the deficiencies are exist on the structure. Okay, after based on that, you can decide what type of the retrofitting measures is required. For example, if your structure has a deficiency on the flexural, deficiency on the shear, deficiency on the axial, or might be the combination of the all above. Accordingly, you can take the call. Okay, that's can classify as a one is a local and one is a global. Okay, in case of this local retrofitting technique, and global modification is shown here. So here this is a local modification part. Okay, in case of the local modification, that increase on the your strength and stiffness still is not significant. Okay, it's not significant, but in case of the ductility, your increment is quite high. Okay, you can observe here. So this is the green color is overall improvement in your ductility capacity, but at the same time, your strength and stiffness, it is not that high. But in case of the global modification, your strength and stiffness increment is quite high, but ductility wise is not that significant. So, okay, so the global modification means is introducing of the kind of the totally a new element like a shear wall and introduction of the use a concentric brace frame or maybe some kind of damping device, and all those things are known as your global modification. The local modification in sense like jacketing of the column and the beam modification, those are known as your local modification. Okay, so that difference you can observe here. So depend on your level of deficiency, you can decide what type of the retrofitting measures can be adopted for your structure. Might be a local or global. So for again, for a local modification, these are the commonly used in a real life, like a concrete jacketing, this steel jacketing, okay, and FRP wrapping. Those are the kind of the commonly used local modification. And in case of your global modification, like this passive energy dissipation device, like your friction damper, viscous damper, okay, and yielding damping device, and the base isolation, and those are the different type of the available that global modification technique, including shear wall modification. Okay, so those you can use it. So similarly, whatever we mentioned like local and global, and all this retrofitting technique, it can be again reclassified based on your material. Okay, one is called the energy absorber and one is called the energy dissipator. And whatever we talk about this fiber concrete, FRP wrapping, and high performance concrete, all are belongs to your energy absorbing category. Okay, in case of the energy dissipation category, like your damping devices, viscous damping device, isolator, all are under the energy dissipation category. Okay, so let's try to understand all these things. Okay, today I'll cover about this fiber concrete and FRP from the energy absorbing point of view. And in case of the energy dissipator, I'll cover all the yielding damping category. Okay. So here, this is the steel fiber concrete. As you already aware that how steel fibers are introduced in the concrete. It is a kind of a short, the small piece of the wire type and mixed with the concrete. And so it increase your impact capacity of the structure, and it control the crack propagation. Okay, and crack in the sense like synchronous crack and all different loading point of view, the different cracks are developed, and all kind of the cracks it can encounter from the steel fiber point of view. Okay, initially steel fiber concretes are used for the mass concreting and the tunnel lining and all, and the road construction. But nowadays, this steel fiber concrete used for the our residential building construction point of view also. And the plus, we can use this material as your retrofitting material. Okay, that I'll show you with the help of the examples and experiment. So these are the market easily available different type of the steel fiber in the market. Okay, so out of this, the second type N hook steel fiber is the one of the is a kind of the best performing type steel fiber compared to the others, and it is easily available in the markets. And another why steel fiber is again predominant in the concrete construction, because it provides extra tensile strength. Apart from your crack control property, it also provides extra tensile strength. And because of that, can you see this figure? So still is intact after having this much big crack, and still structure is intact condition because of your fiber bridging action. And if you look here, this is the compressive behavior of the concrete for the plain concrete, as well as you can observe similar thing. But in case of the plain concrete, this tensile part, it is usually ignored, and it is the very low tensile capacity is there. But here, in case of the steel fiber, still it has a very high tensile capacity. And one of our study evaluated this tensile capacity. And here, if you look, this is a 3-point bending test. Okay, this is, and COMOD, okay, crack mouth opening displacement device is attached here just to check your overall tensile capacity of the steel fiber. And if you look here, this is a different type of the mix starting from the 0% and 0.25%, 0.5%, 0.75%, 1%, and this 1.5, 1.25, 1.5, 1.75, and 2%. And in case of the 0%, just after reaching the peak load, the specimen is broke, and the similar behavior still you can find at 0.25%. From 0.5 onwards, the members are not splitting. Okay, still under the, after reaching the peak load, and still they are in intact condition. But in case of this 1.25 and the 1.5 range, the only cracks develop, and still the specimens are in the well and good condition, and up to the 2%. So that's the benefit of your steel fiber concrete compared to your plain concrete. And that's why this steel fiber concrete shows its superiority in case of your retrofitting compared to your plain concrete. And here you can observe this is the increment of your tensile capacity. Okay, here 10 times 1.1 times compared to your plain concrete in your steel fiber concrete, and sometimes up to increase 20% to 30% is increase. Okay, starting from 0 to 2%, the increment variation is from 10% to up to 30%. But optimum range you are getting from 0.5 to up to 1.5% is your optimum range you are getting. Okay, so I'll just make a small conclude here. If you want to use steel fiber in your construction, better to opt from 0.5 to up to 1.5. The best is, again, among this range also, the 0.75 to 1% is again the best optimum range, because it will not create any your workability issues. But if you provide more than 2, instead of improving, your concrete quality is going to be degraded. Okay, it did not mean that whenever you increase the fiber percentage, your concrete performance is keep increasing. Nothing like that. Your concrete performance will be the best performance when the steel fiber range starting from 0.75 to up to 1. But of course, it has a wide spectrum from 0.5 to 1.5. But within that also, optimum range is 0.75 to 1%. Okay. Based on this finding, we start using this material for the retrofitting purpose, and we construct a 1 RC frame. Okay, only the ground, single base, single story, and this is a non-ductile category concrete. And this the light blue highlighted zones are a plastic hinge zone. Okay, it's a highly potential for damage, and only in this zone itself we put the steel fiber concrete, that to 1% steel fiber. Okay, from the material characterization, we came to know that those are the 0.75, 1% as the optimum. So we put 1% concrete, steel fiber concrete here. So this is the during the construction phase, we identified those things, and pouring those, casted those type of steel fiber concrete, and perform this extra specimen under the cyclic loading test. Here you can have a look how the specimens are behave under the cyclic load, and this is for this is for plain RC. Okay, steel fiber is not introduced in this frame. Only the plain concrete used for this frame construction. And you can see many major cracks are appear in the structure. And this second video shows this is a still fiber concrete. Okay, so the structures are identical, only difference is in the plastic hinge zone we put the still fiber concrete. So if you look here closely, here the multiple micro cracks are there, but in case of the RC, it has a major cracks. Okay, so here you can see all are the major cracks, single major cracks are appear in case of the your plain RC frame, but at the same time, the still fiber concrete specimen has multiple micro cracks. Okay, but not the single major crack. But in case of the your this the plain concrete RC frame, the minor cracks are less, but only single major cracks are there. This is very critical. Okay, so most of the your structural instability will starting from such type of the single major crack. Okay, the micro crack shows that it absorbs your most of the lateral force energy. So this is a comparison of the that both still fiber and this plain concrete specimen comparison. You can observe in case of the still fiber, it has a good energy dissipation capacity. Also, it has a higher lateral resistance capacity. So it shows clearly both the still fiber can be used as a your retrofitting of the dismember. And what are the beauty of this? So if you use this one without changing your cross section dimension, simply replacing the existing concrete by still fiber, your structure can be renovated. Okay, so it means you will not lose any kind of the space. But if you try to provide some kind of the other jacketing and all, your size of the column is going to expand, size of the beam is going to expand, so you will lose some of your floor area. Okay, so especially when you have this marginally some the demand is small and all, that time still fiber concrete will be a solution for your retrofitting. So similar kind of this study we extended. So the one which I shown, that is for your frame level. So now closely we'll try to monitor what are the behavior of this beam column joint junction. So beam column joint is one of the most critical part in your reinforced concrete structure, because it has maximum shear force and maximum bending moment is in the beam column junction. So because of that, you'll have a very high percentage of the concrete reinforcements are there. So it is difficult to pour concrete sometime. Okay, so by introducing the steel fiber concrete, because steel fiber has a shear capacity as well, so if we able to reduce some of the longitudinal reinforcement, and that is the motive of this study. So we able to compensate something, and we develop a different reinforcement configuration by replacing the some portion of the reinforcement by steel fiber concrete. So we observe some improvement on that. That result is highlighted here. Yeah, these are the different damage pattern of the those steel fiber, different type of steel fiber concrete. So the plastic hinge zone is shifted here. This is well kind of the development in case of the your steel fiber concrete that to in the beam column joint. So similar study again we extended for a coupling beam, and you might know that what is a coupling beam is the beam connecting between the two shear walls. Okay, the shear walls are highly a slender, tall structure. When it moves under the one in plane, the connecting beam, coupling beam has a high shear demand. Okay, so in that beam, most of your energy is dissipated through that, and because of that, sometimes your bar fracture is happening in the junction. So those bars failure, it is quite complicated for retrofitting. So because the anchoring will not work properly. So in that point of view, we just modified the overall reinforcement in the double behavior based reinforced configuration, and we introduced the steel fiber. Okay, so here we did the two specimen, one is the RC and one is the steel fiber, and we did the both comparative study under the cyclic load. So this we can see how this coupling beam behave under the cyclic load. So here we did the two specimen, one is the RC and one is the steel fiber, and we did both comparative study under the cyclic load. So this we can see how this coupling beam behave under the cyclic load. So, Yeah. So this specimen got damaged extensively, as you see here. So this damaged specimen we make in such a way that because we want to retrofit it. So our intention is for the coupling beam, how to retrofit after extensive damage. So after having this much damage, there was no any bar ruptures are not observed. So we repair and retrofit this specimen with the help of this steel jacketing. Again, we repeat the same type of the study, okay, experimental. And this work is well appreciated from a different section of the people. And recently we published this work in the Journal of Structural Design and Construction, ASE, so that you can observe here. And now this is the first section of the your energy absorbing material as a steel fiber. In case of another material FRP, the fiber reinforced polymer, this also another absorbing material. That let's discuss hardly around another 5 minutes on this. Okay, so FRP has an advantage in terms of the high mechanical properties and its moisture resistance, and it's a very lightweight material. But disadvantage is a very sensitive to the heat and is quite expensive. Okay, and I mentioned that high mechanical property. So what is the meaning of high mechanical property? So when you look to the this one design course for your reinforced concrete structure design, usually what currently we use is a FE 500 at this moment. Okay, currently FE 415 is not available in the market. So FE 500 means it is the 500 MPa is your yield stress. Okay, in case of the FRP, the 500 is nothing. Okay, it yield stress starting from the 750 MPa and it goes up to the 2500 MPa. So usually the market, the available FRP in the market is around 1300 to 1500 MPa is a yield stress. It means 3 times to 4 times higher than your conventional reinforcement what currently you are using in the construction. So that's why FRP has a great advantage in case of the retrofitting, because it is a very thin sheet cloth type and it will not occupy much space after retrofitting of the structure also. Okay, so FRP can be used for a single purpose, like for only for the flexural strengthening. Okay, only for the shear point of view. Okay, either combination of the your flexural and the shear, or might be only for your axial. Okay, it means FRP can be, I can say that it's a multi-purpose. You can use it either for flexural or maybe shear or maybe the axial or combination of the all. So but accordingly you need to decide what is the orientation of the your wrapping. In case of the flexural, you need to wrap just below the soffit of the beam. So it will work as a extra reinforcement, addition of the reinforcement from the whatever your reinforcement below the beam, the FRP will act as an extra reinforcement on that. Okay, so in case of the your this shear strengthening, you need a wrap either on a side by side face or maybe in the U type wrapping or maybe the full type cross section wrapping. So that will enhance your shear strengthening. So in case of your column, depend on your biaxial demand and the axial demand, you need to wrap the FRP, the different number of the layers need to be wrapped, maybe single layer or double layer. So here this diagram shows that initially your structure got damaged in the shear. So from our structural point of view, we don't want any shear kind of damage at any condition. So after wrapping the FRP, this shear deformation type, it will be transformed to the your flexural mode deformation. Okay, so that things can be so those things possible when you are doing the proper design of this FRP. Okay, so for FRP design, currently we are using the ACI 440 is the one of the code we are using, and here you can see one of the that concrete has a low axial load carrying capacity. This is a buckling of the reinforcement. This type of the buckling, the FRP give a perfect solution on that. Now here you can see this is the after retrofitting. So that damaged part, it was with the help of your extra reinforcement, it just provided enough strength. After that, we provide the FRP. So there will not be any more buckling in future in such retrofitting. So again, from our side to validate similar kind of the retrofitting, we just perform experimental on open ground story building. If you look here, this is one of the critical damage on open ground story. Shear damage is observed, and this loose portion concrete we remove here. Okay, we remove, and we have the epoxy, a layer of the epoxy provided, and the some micro with the help of the micro concreting, the surface preparation has been carried out. After surface preparation, we perform this FRP wrapping, and as I'll tell you, before wrapping the FRP, first of all, after this surface preparation, you need to make a rounded shape at these edges. Okay, so once after your casting your concrete, this column surface, especially in the edges, it will be very sharp right angle type edges. Okay, so that should be avoided. Okay, with the help of some other mechanical device, you need to make as a rounded, with the help of the around 1/10 of the depth as a radius, you should make it. Okay, so according after that, you have to provide this FRP wrapping. So we did on open ground story building. Let's have some short video how that frame is behave after the FRP wrapping. Okay, you can observe from here. Yeah. Okay, so after reaching to the almost 3.5% drill, the steel structure is not collapsed, and it is a good strength is shown here. Yeah, you can see here at the after reaching that 3.5% drift, still your structure is in a well and good condition. Only some few cracks are observed here. So this is the hysteresis you can observe. It is reaching the 3.5%, and we had a target of 4% drift. Of course, the structure can reach to 4%, but because of our test setup limitation, we stop experimental at the 3.5% drift. But I'll tell you that as per our seismic code, permissible drift level for the RC, this one reinforced concrete structure is a 4% drift. Okay, it's a 4% drift, but in case of the open ground story, it will collapse. Usually it collapses within the 1%, maximum around 0.5, 0.75, that range it's collapse. So as I mentioned, the 10% of the your this one drift is 4% of this drift is allowed, but forget about the 4%. It is collapsed in a 0.5% and 0.75%. So the performance of the open ground is typically quite weak. So after this FRP provide, now it's easily reached up to the 3.5% drift level. So it's a kind of a great achievement in case of your open ground story point of view. So here is the from the energy absorber point of view, I covered this steel fiber and this FRP. Now let's have a look on the energy dissipation device. As I mentioned in the beginning, dissipation device are like friction damper, viscous damper, and base isolation structures. Okay. Again, yielding damping device is classified into three category. One is your flexural yielding device, shear yielding device, and axial base yielding device. Okay. So flexural base yielding device has, I'll talk about this yielding base criteria, friction damper, viscous damper, and isolators. I will not cover in this talk. So in case of this flexural yielding damping device, it has a great ductility. Okay, but your strength and stiffness is still in the lower sides. So when you talk about this shear yielding link, it has a great strength and stiffness, but it has a limitation on the ductility. And similarly for your axial base like BRB or maybe the brace configuration, and the concentric brace has a limitation on the buckling, that we know that. And in case of the BRB, it is performing well under the cyclic load, both in the push, compression and tension, but it also has some limitation in the ductility, and the necking failure is one of the major concern. So considering all those things, I'll show you what are the device we develop. Consider. So as I mentioned in the concentric breast frame, this is one of the very classical base damping device which used in the hundreds of years. We are using this one, but the limitation of this device is your buckling. Okay, so here you can see in this diagram, the device is behave very effectively under the tension part, but the moment when it comes to compression, it suddenly lost the strength. So it's introduced instability on the structure. So that's how overall stability of the structure might lose it. So how to counter this one? Of course, we know that the bracing system is one of the most effective one. So, but the buckling is a major concern. So introducing to that, okay, before moving to the BRB, let me show you some of the concentric breast frame video. I just show here. Yeah, that the buckling behavior clearly you can observe here. So this is some of the experiment that we carried out in the laboratory. And this is the sub-assembly level and how we perform. Okay, so this fella. So especially if you really want to use this concentric breast frame in your retrofitting of the structure, just please try to take care of this gusset plate connection. Okay, so sometime in the beam column junction, your concentric breast actually touching to the beam to column junction. So which is not acceptable, because once if you touch to that point, whatever the extra bending moments induced from your concentric breast, again it will be another demand on the beam column joint, because the beam column joint is already in the critical. So now after providing this one bracing, the bracing should not be introduced any more extra moment on that. Just to avoid that, you have to design a gusset plate properly, and this you should maintain this a clear gap here. This clear gap is known as a yielding zone. Okay, so with the help of this yielding zone, your all the bending demand is going to be dissipated here. Okay, so most of us is underestimate this part, and we are not. See, if you look to the IS code, all IS code, you will not find such kind of the criteria. But this is a recent development, so you need to provide a yielding zone, especially when you use this concentric breast frame to release your extra bending forces demand that you can observe here. So in this photograph, all these concentric breast frames are not touching to this junction. It is stopped here, and these plates are keeping as a empty here, because this is the yielding zone. Okay, we are allowed to damage here. So if we are not provided this one, the damage will be occurring in this your junction zone. Okay, which is very critical. So be careful about when you use this concentric breast frame. So as I mentioned, this is the one of the portion yielding zone based experimental we carried out in the laboratory. You can see here the clear yielding zone is visible here. So as I mentioned, the limitation of those concentric breast frame and how to overcome of that bracing that's shown here. So this is the BRB structure. Okay, in case of the BRB, it control your overall buckling behavior. These are some of the specimen we perform experimental in our laboratory, and we provide this covering as a concrete covering we provided here. And this is a test setup we use for this development of this BRB. And have a look this hysteresis behavior. Okay, in this hysteresis behavior, you can see both compression and tension. It is identical. But previously, what I saw for the concentric breast frame, one side was quite strong and one side was quite weak because of the buckling behavior. So that buckling behavior is disappear in this device. Okay, so this is a superiority of your BRB, but only limitation of this BRB is a kind of a necking zone failure. Okay, so this is a kind of the critical part, and but lots of advanced materials are here like shape memory alloy and all, just to avoid that. And this is some of the findings we presented from our research work. So you can see before and after how the BRB samples are damaged here. Yeah, this is a sub-assembly test for the BRB. Yeah, the failure of that BRB you can observe here. Yeah, so the BRB and this concentric brace frames belongs to your axial base yielding device. And now, as I mentioned, let's talk about this shear yielding damping device. As I mentioned, shear yielding has a great initial stiffness and strength, but this ductility wise, still it has a limitation. Okay, and in case of this, your flexural base, that also I mentioned that it is a good ductility but low strength and stiffness. But for the ideal device for retrofitting, you need to have all the three parameters: strength, stiffness, and ductility. So if you have all these three parameters, by default, your energy dissipation capacity will be very high. So, but the limitation of this flexural and this shear link also always compromise in your energy dissipation device, energy dissipation of that device. So considering that, okay, I'll just skip this portion. Okay, this is for your flexural base. Yeah. So considering those device limitation, I develop one device for open ground story that I'll present it in the next slide. So now let's try to understand what are the issues in this open ground story building. And open ground story building, one of the retrofitting technique also I have shown it, but here let's try to see the open ground story is one of the most effective building in terms of your functional point of view, but is one of the worst performing structure in terms of your performance point of view. Okay, structural performance, it is not acceptable, but from the functionality point of view, this is one of the best because it has a car parking facility, your storage facility and all. So that's why still after having the low performance, but people still has a high demand on this type of structure. So we need to provide a solution on that. And this type of the typical failure in open ground story is known as a soft story failure. Okay, so why these soft stories are quite critical? So if you look in the structure before putting the masonry wall, the structure is known as a frame mechanism. The moment when you put the masonry wall, the frame mechanism converted to a truss mechanism. But in case of the open ground story, you have a combination of the truss mechanism and the frame mechanism together, and it has a very high displacement demand at the first floor. That's the one of the main critical point of the open ground story building. And if you look, these are some of the typical failure mode of the open ground story building in the past earthquake. The first one shows the Manga earthquake. Here, the ground columns are tilted, but superstructures are quite well and good, no damage. And the second one is from the Northeast earthquake. You can see how the structures are collapsed. And the third one is from the Bhuj earthquake. You might have seen the structures only tilted. But if you look here, this so the surface level and this one beam level, there is a one ground column part is already crushed. Okay, actually the beam level you have seen here, this is on the first floor level. But here you have observed is like kind of a ground floor level. So this is the kind of typical mode of the failure in the open ground story. And in the Bhuj earthquake, total 150 open ground story building got collapsed. Okay. So what are the major issues in those open ground story? It has a insufficient lateral strength, insufficient stiffness, and a limited ductility. So as I mentioned, for the shear yielding as well as the flexural yielding, it has its own advantage in terms of strength, stiffness, and ductility. But both devices don't have all the three parameters. But if you look here, open ground story, all these three parameters are really needed. So we need to bring some solution which have all the three parameters from a single device. So based on that, my team has developed one device called a combined metallic yielding damping device, which is a combination of your shear plus your flexural, both the device mechanism, and it provides both strength, all three parameters, strength, stiffness, and ductility. So it has a good energy dissipation capacity. So here is a component level testing. You can see what are the different type of hysteresis observed here. So just to validate the effectiveness of that device, we took a prototype building, open ground story, and we installed this damping device, and we carried out a numerical study as well as a experimental study. So in case of the experimental study, you can see here, this is the construction phase. So after completion of this open ground story, we installed this device. We carried out our El Centro ground motion. We perform it with the help of the pseudodynamic testing. And after that, we carried out another collapse level testing also. You can see here how the structures behave during that collapse level testing. Yeah, so you can see this is a close view of the that damper under that same frame. This is the only focus on that damping device. So this is at the end of the experimental, how the dampers got damaged and what are the critical damage observed is here. So your open ground story structures has a very limited pinching behavior, and it shows the up to 2.3% drift is able to reach it. It's another great achievement. So it means you can say that the CMD device is able to solve your soft story mechanism. Okay, that too with great energy distribution capacity. But in case of the other FRP or some other material, you are reaching with the ductility, but the energy dissipation capacity is still in the lower side. But here, energy dissipation capacity is in the much more higher sides. You can see here, those are the stiffness and energy dissipation variation here. Yeah, again, this is the atypical hysteresis behavior of your damping device during that the collapse level testing. And similarly, just to check the effectiveness of this device in the two different category of the building, this one installation we carried out in a single story building, one in this chevron condition and one is a inverted chevron configuration. Let's have a look how it looks like under the experimental this one cyclic load testing. Yeah, even in this configuration also, this device effectively perform. Okay, it is the performance is achieving all kind of your requirements achieved without any instability on the frame. Okay, that you can observe here. So in the second one, you can see this. So here also, here the devices effectively work in initial phase, but after some time, because of your connection failure, the structure is the damping device is not effectively work it. Yeah. So means connection is one of the most important parts in this damping device. So before installation of the device, we should be very careful about this connection. So after we know that device work effectively, but if your connection is not significantly strong, then whatever your device, it will not activate it during this seismic event time. So this is your we did a retrofitting using the FRP energy absorber, and with the help of the damping device, we again retrofit this open ground story that you observe it. Again, another third category of the global modification, introducing the shear wall, we can retrofit the open ground story also. So here you can have a look as a short video of this introducing shear wall in the open ground story. Yeah. So overall frame movement you can observe from here. So again, this also showing a very great power of this one estimate. Okay, in terms of your energy dissipation is little lower side, but strength and stiffness and also ductility is with high capacity. And now I can make a some summary on this all this material what I use for the retrofitting. In case of the steel fiber, it reduces your congestion of the reinforcement. It enhances shear strength. It improves ductility, and it also control a crack. And in case of the your lower fiber content, okay, 0 to 0.5%, multiple cracks form and instabilities or mildly controlled. And in case of the your SFRC 1.25, it shows around great improvement. It's a kind of the one of the optimum range, and higher 1.5 and 2, it has a good performance, but it has a limitation on your workability point of view. So means the optimum range of the your steel fiber is, as I mentioned earlier, range from your 0.5 to 1.5 is the optimum range, but within that also 0.75 and 1 is the one of the best option for you. And in case of the FRP wrapping, it enhances your drift capacity, okay, without any making instability on the structure. And the failure mode is shifted from your shear mode to the flexural mode is shifted, and which is required for your open ground story building. And energy dissipation capacity is moderate. It shows up to around 25 kilonewton and reduce the pinching behavior, and it preserves the floor space because it is not losing any floor area. And in case of the energy dissipation, it works as a fuse, as we know that after the earthquake, that device will cut out and we'll put another new one. So the structure will be again regain the normal condition. So that's why it works as a fuse. And it has the highest energy dissipation, and it mitigates the sub-story mechanism. And the connection detailing is the one of the very critical area that need to be take some extra precaution, and adaptable for retrofit for both new construction as well as the all retrofitting structure. Okay, and it's a kind of the minimum downtime post disaster properties we have. Okay, it's easy to replace and it's easy to install also. Okay, this is the overall conclusion from this my talk. And if you have any things, we can have a short discussion here. Thank you.
Thank you, sir. We will wait for the participants to for the questions if they have any. You can also, participants, you can also write the questions in the chat box if you want to. Ma'am, would you like to say something? Verma, ma'am.
Thank you, sir,
Yeah.
for your very.
Thank you, ma'am. I think audience don't have any question. So
Yes, we are waiting for the response from the audience, from the
okay.
participants. Or else, sir, we will share your email ID. They can even ask further for
Yeah, they
immediate.
can contact to me. No issue there.
Yes, sir.
So then, shall we wait for some few minutes or shall we close the session?
So I think participants are praising you. They are giving thank you for your
Okay.
informative session, sir. Thank you so much, sir, for accepting our invitation.
Thank you, ma'am.
Thank you. Yes, sir. Thank you, sir.
Okay. Okay, then I'll leave the session, madam.
Yes, sir. Yes, sir. Sure, sir.
Okay.
Ma'am, would you like to explain to the participants what to be done now?
I think we can share the link, test link, and time is 6:22 right now, or we can wait for another, 6:30. Can we hear it from participants? Shall we wait or shall we start the test? Okay, so I think we can start with the test.
Yes, ma'am.
I request Rishikesh sir to please share the link with the participants in the chat box.
Okay, ma'am. Yes. Okay. The link has been shared. We will end the test at 7. So 6:23 now.
Last 5 minutes left. Again, we are requesting participants to please reply, submit your test, because it is not possible. After 7, we cannot open, or we could not open it. The link will be automatically disabled after 7. Please make sure that you have submitted your test. Those who have submitted, thank you so much. And please be remain for the validatory session. We are going to start the validatory session in another 4 minutes time. Please be there, because attendance in the validatory session is also mandatory. Yes, participants, you may please submit the feedback in the AICT Atal portal. You can submit it from your end. Individual participants can submit your feedback on your portal. Please do submit your feedback. Thank you, Dr. Akshay. Thank you so much. Sorry, ma'am, we cannot extend it for another 15 minutes. That is not possible. We have to close it, and the validatory session will be start very soon in another 3 minutes time. Sorry for inconvenience, but we cannot do that. Yes, please submit your feedback in your AI Atal portal also, in which you have already registered as a participant. Please do not send me individual messages, because it is difficult. I'm flooded now with all the messages. I cannot do this favor, because it is not, we are bound to close this as early as possible. As you have also heard that one of the participants are requesting for the releasing of the certificate. So certificate will only be released when I entered all the marks in the portal. Then only you will get the certificate. So that marks entry will be done on at my end. So please make sure that you can submit your paper. I cannot do any favor in that. Please be understood. Yes, yes, sir. Please go ahead with submission of your feedback on a portal. And we are also requesting in a validatory session, we would request you to please switch on your, unmute your mic, and you can give your feedback there itself. Those who have submitted, thank you so much. We have received 88 response till now. I'm requesting other participants to please respond it quickly. I'm not sure about the maintenance, sir. I can, right now I can access the portal. So It was only for the day of 25th. I can access it now. So I think you will be getting the certificate maybe tomorrow or day after tomorrow. Once I have done with all the requisites in the portal. Thank you so much, ma'am. If you have submitted your test and feedback.
Madam, we have closed the test now.
Okay.
7.
Just 2 minutes. I'm just submitting now. I'm at the end of the test. Only 2 questions are left.
Rishikesh, can we just another 1 minute time we can give?
Okay. Okay.
Please make sure submit it in just 1 minute time. We are just extending it to 1 minute. Please submit it again and again. I'm repeating the same. Please submit it. Do submit your test. As you have got enough time to submit it. It's only a multiple choice question. No, there is no other test, sir. Only one test. This is the last one. And the feedback form. That's all. Nothing else you have to do. So please make sure we are closing it now. Please submit it. We are closing it now. I request Rishikesh sir to please close it because we will straight away going forward for the validatory session.
It's closed, ma'am.
Okay, so we go ahead with the.
Sorry, ma'am. I'm just disturbing you again. I submitted, but now it is saying ki, we are sorry, this document is not published. Can you just check it whether my submission has been accepted or not of the test?
Right now, 93 participants have submitted. I can see that. I have not checked it individually, but you have submitted. You will get the score straight away.
Yeah. I have submitted, na, because here is something showing different. That's why I asked, ma'am.
No, I'm not sure, sir. I'm just saying that 93 participants have already submitted. I cannot see the individual one right now.
Okay, this document is not published. It means I think it has submitted maybe. Normally it will show ki it has submitted. That's why I'm saying.
Hello.
Fine.
Yes,
Good
sir.
evening. Sir, I submitted and I show my score.
Okay, you can see your score, right?
Yes, ma'am. It
Yeah.
says that 43 out of 50.
No issue. Thank you so much. Thank you. So, sir, from your end, it might be some problem, network issue, because
Yeah.
please can submit it. I can see that 93 participants have already done.
Okay,
Oh,
then
okay.
what should I do, ma'am, in my case? Because I again refresh. No, this document is not published. It is showing again.
Fine, sir. We will see to it. No issue. So, Christy, over to you.
Yeah. So as we head to the valedictory of this 6-day FDP, Atal AICTE sponsored FDP, I here request Professor Dr. Shatambara Verma, Department of Civil Engineering, to address the participants with your closing remarks.
Thank you, Christy. Now we are going ahead with the closing of this FDP ceremony, which was held for 6 days online session. I'm starting with day 1. Day 1, session 1 was held. Dr. Hemanta Kaushik sir was taking that session. It is on performance of different building topologies in India during earthquakes. The session emphasized on the non-engineered and poorly detailed construction remain highly vulnerable to earthquake damage, while traditional seismic friendly building systems in India, such as bamboo or timber, often shows a better resilience than poorly designed modern constructions or structures. The importance of strict code enforcement, retrofitting existing building, and spreading awareness was highlighted as essential steps for improving the seismic safety in the country. In that day one, another session comprising of importance of intellectual property rights in civil engineering by Dr. S. Vardharajan. So it was highlighted that the intellectual property rights play a vital role in protecting innovations such as advanced construction materials, patented systems, and green technologies. By ensuring that innovations are legally safeguarded, IPR not only motivates further research and development, but also fosters sustainable growth in civil engineering sector. We have day 2's session 1 comprising on structural monitoring repair from detection to corrosion by Dr. Aparup Bishwal. This section underlined the importance of a systematic workflow for addressing structural deficiencies, beginning from detection and diagnosis to decision-making, deployment, and final documentation. The use of non-destructive testing and advanced tools like FEM was emphasized for accurate assessment, ensuring that repairs are both effective and long-lasting. Then we have on day 2, the session was on sustainable reinforced construction using bamboo by Dr. Nayanmoni Shetya ma'am. The discussion showcased that bamboo as a promising or sustainable reinforcement material, highlighting its renewable nature, tensile strength, and environmental benefits. Traditional bamboo house such as shangas were analyzed and demonstrating resilience and sustainability, while modern treatment methods like joint designs were presented as a way to further enhance performance in structural applications. Then moving on to day 3, we have session 1 on numerical modeling for seismic soils in structure interaction by Dr. Kaustav Dasgupta sir. The lecture emphasized on soil structure interactions plays a pivotal role in determining structural response during earthquakes. And it was noted that the soil properties, foundation type, and seismic wave propagation must be modeled realistically using advanced tools like finite element methods, and ignoring SSI can lead to unsafe or overly conservative designs. The session 2 continued with the same resource person, Dr. Kaustav Dasgupta. The session was on importance of floor slab in seismic behavior of RC structural wall. This session highlighted how floor slab influence in seismic performance of RC shear walls by subdividing walls into story panels and altering into the load transfer mechanism, which was
Alan, can you unmute yourself? I think. Yeah.
So am I audible now?
Yes, ma'am. Yes.
Yes,
So
ma'am.
is it in the beginning I have to start, or?
No, 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 ma'am. Just
From the beginning, it is audible, ma'am.
Okay, fine. So we are on the session day 3, I think so, right?
Yes, ma'am. Yes.
Okay, so day 4 session was on seismic vulnerability of infrastructure and resilience planning. The session was given by Dr. Arjun Sil sir, and in that session, the seismic risk is a function of hazard vulnerability was emphasized, and its exposure, and how to encourage engineers to adopt fragility modeling and promote green and sustainable infrastructure, which also integrate resilience planning into in terms of earthquake and earthquake-prone zones in order to mitigate the disaster. The session, day 4, second session, was on seismic vulnerability assessment of structures by Dr. Kaushik. And it was explained in that session that probabilistic and deterministic methods are very essential for reliable vulnerability assessment. Non-linear pushover analysis was presented as an effective tool to evaluate structural capacity and performances. Day 5, we had the session 1 on insights from to 2025 Myanmar earthquake and their implications on Northeast India. The session was presented by Engineer Vinay Karna. The session emphasized on the potential for complex and large strike slip ruptures in that region, and also along with the secondary hazards such as liquefaction, landslides, and ground failures that further worsen or damage the property. For northeastern India, the key lesson is to reassess the hazard assumptions. The codal provisions has to be implemented and incorporated in the design right from the very beginning, and strengthen the critical lifelines, enhance cross-border coordination to prepare further large events related to this hazards. The day 5, we had a session on ultra high performance concrete. Session was by Dr. Ketan Ragalwar. The session introduced the ultra high performance concrete as a next generation material offering very high compressive strength, tensile capacity, and durability. Despite higher cost and special requirements, UHPC offers us long service life, reduced maintenance cost, and its application in critical infrastructure make it more suitable and sustainable for future construction. Today we have on day 6, the first session was on structural health monitoring by Dr. Nirmalendu Devnar sir. And the session highlighted on structural health monitoring practices for modern infrastructure, enabling early damage detection, reduced maintenance, and extended service life of the structure. The integration of sensors like fiber optics, artificial intelligence, IoT, and big data is set to revolutionize the real-time monitoring system, especially critical in seismic and disaster-prone region like northeastern India. We have on day 6, session 2 by Dr. Leonraj sir on a failure of reinforced concrete deep beams. And in that session, it was explained that the reinforced concrete deep beams behave differently from shallow beams, transferring loads through compression, struts, and tension ties. Failures such as diagonal shear cracking, flexural yielding, and bond failures were discussed in that session. And with strut and tie modeling, it was recommended for accurate design assumptions, critical element like pile caps, transfer girders, and bridge components. We can have such failure mechanism to avoid the risk. Then on same day today, we have third session on retrofitting of non-ductile open ground story buildings using yielding damping devices. And also the retrofitting mitigation methods was discussed by Dr. Roman Babu Oniam sir. The final session of today, and it was emphasized in that session that earthquake due to soft story effect, how we can mitigate and are extremely vulnerable in terms of earthquake point of view. So yielding damping devices were presented and effective retrofitting strategies were discussed, which is capable of dissipating the energy, and it is energy absorbable, enhancing the ductility of the columns and the material. And this is a very cost-effective solution highlighted by Dr. Raman Babu Oniam sir. In summary, overall, this FDP gives a clarity by combining the traditional wisdom with the modern materials, advanced analytical methods, innovative retrofitting strategies, and sustainable practices. We can build a safer and more resilient built environment, particularly vital for the earthquake-prone zones like northeastern of India and also the cross border, like Myanmar, Thailand, Bangkok, and all other which are very prone to seismic vulnerability. So with this, I'm going to conclude my session. Thank you so much for all your patient listening and hearing, and for active participation. Over to you, Christy.
Yeah, thank you, ma'am. Now, as to conclude with a note of gratitude, I request Mr. Rishikesh Dwara, Assistant Professor, Department of Civil Engineering, Co-Coordinator, to address the participants with his vote of thanks.
Thank you, Christy. Good evening, everyone. On behalf of the organizing committee, I extend our sincere thanks to each one of you for being part of this faculty development program from start to finish. We are grateful to AICTE and the Atul Academy for the grant and for their steadfast support faculty capacity building. My heartfelt thanks to our invited speakers and resource persons for the depth and clarity they brought to every session. Your lectures, demonstrations, and discussions has given us practical ideas we can take back to our classrooms and labs. I also thank our university leadership, especially the Vice Chancellor and the Dean of the Royal School of Engineering and Technology for their encouragement and guidance throughout. A special word of appreciation to our coordinator, our faculty members, technical team, and our student volunteers. Your quite precise work kept the program on track. To all participants who joined us from various institutions, thank you for your active engagement. Your questions and reflections enrich the dialogue and the outcomes. Before we close, kindly ensure your feedback forms are submitted and certificates will be issued accordingly. We will also share the resource links and any follow-up instructions via email. With deep gratitude to everyone who contributed to this FDP, I now formally conclude the valedictory session. Thank you and wish you all continued success.
Thank you so much. So, well, we can end this meeting. However, ma'am, is it should we take a photograph?
Yes, we can request participants to unmute themselves and can share their views,
if you have any. Or Jay, are you there?
Yes, I'm here.
Yeah, if you're there, just click a photograph of the participants.
Sure.
Hello. Hello.
Yes, sir. Yes, sir.
Should I speak?
Yes, sir. Please.
Yes.
You are...
Congratulations to Mrs. Verma, Dean Civil Engineering, Assam Royal Global University. At this conclusion, I wish extend my warmest congratulations to you and your entire team for organizing a highly successful and informative event on seismic vulnerability assessment, earthquake assessment in Indian context, and USA techniques. Your efforts bringing together renowned experts and providing a platform for knowledge sharing are truly commendable. As the great Nelson Mandela once said, the greatest glory in the living lies not in never falling, but in rising every time. So I am thankful for your uh, valuable information for this seismic vulnerability. Thank you very much. Thank you.
Thank you, sir. Thank you so much for your valuable feedback. May I now request other participants to please share some few words on this FDP.
Madam, can we submit some international conference on it?
Sorry, sir.
Actually, my kids are in USA. So can we submit some international conference on this topic by your collaboration?
Sure, sir.
Okay, we'll think on and we'll submit the international conference on it.
Okay,
Thank
sir.
you very much. Thank you.
Sure. Thank you.
So thank you, everyone. So with this, we conclude this 6-day journey. Have a great Puja holidays and good night.
Now, ma'am, just one question I want to ask. I have submitted the assignment. Still,
Okay.
I am getting that answer only that on my screen. Just you check it at your end also.
Okay, we will respond to you, sir. You can
Yes.
personally send your message so that we
Yes.
keep reminding.
Okay,
And
ma'am. That I will do. I will
we
do.
will,
Definitely, I will do.
for other participants, as I can see in the chat box, the YouTube link is a playlist basically. So day-wise, you will be getting all sessions recording into that. You can even like that. I'm not saying here, but you can like that, because anyway, those who are like in your contacts, if anybody is there, you can share it with them also, because it is just a spreading of knowledge.
Thank you, ma'am.
Thank you. Good night, everyone.
Good night, everyone, with this. Thank you.
Thank you. Jay, you can end the meeting.